Imagine something so huge, so powerful, and so intense that it makes our sun look like a tiny spark. Now picture this monstrous star burning with such fury that it could blast entire solar systems apart. This isn't science fiction, it's real. Somewhere far out in the universe, astronomers have found the biggest and most terrifying star ever discovered. Its size, heat, and energy are beyond anything we can truly imagine. Before we begin this journey, let us know where in the world you're watching from and what time it is for you right now. Drop it in the comments below and settle in for a fascinating exploration through space. When we look up at the night sky, we see little twinkling dots. They seem so small, just tiny pinpricks of light scattered across the darkness. But those little lights are actually gigantic, blazing balls of fire, cosmic furnaces filled with violent energy. Inside them, powerful nuclear reactions are constantly taking place. These reactions create the energy that lights up galaxies, allows planets like Earth to exist, and even bends space and time itself with their gravity. But not all stars are the same. Some are calm and steady, like our own sun, which has been shining peacefully for about 10 billion years. Others, however, are unimaginably massive, true giants of the universe. These enormous stars shine so brightly that they could easily swallow entire planets and still hunger for more. They're not just bright, they're terrifyingly powerful. So what exactly is a giant star? In astronomy, the word giant isn't just a way to describe something big, it's actually a specific stage in a star's life. After a star has used up all the hydrogen fuel in its core, the fuel it has been burning for millions or billions of years, it begins to change. It starts fusing heavier elements in a shell surrounding its core. This new kind of fusion creates a powerful outward pressure that pushes the star's outer layers far into space. The star begins to swell, growing hundreds of times larger than it used to be. This stage is called a red giant, and it looks like a bloated version of the star's former self. For stars that are much bigger than the Sun to begin with, this process becomes even more extreme. These grow into red supergiants, and in rare cases into hypergiants, enormous celestial beasts so massive they could cover entire solar systems. But how do scientists measure something so unbelievably huge? Astronomers use special units that are hard for most people to imagine. For example, our Sun has a radius of about 696,000 kilometers. That's already enormous. But take Betelgeuse, a famous red supergiant. Its radius can be up to 900 times larger than the Sun's. If you placed Betelgeuse where our Sun is now, its surface would stretch far beyond the orbit of Mars, yet even Betelgeuse is not the biggest. There is another star called WHG 64 that dwarfs it. This colossal star, a true cosmic leviathan, may have a radius up to 1,540 times that of the Sun. That would make it large enough to stretch beyond the orbit of Jupiter if it sat in the centre of our solar system. Imagine a single star swallowing half the solar system. That's how huge we're talking. But a star's terrifying size isn't its only frightening trait. There's also its brightness, or luminosity, which is the total amount of energy it gives off every second. Our Sun produces just the right amount of energy to warm Earth and support life. It's a steady, reliable star. But the largest stars? They produce hundreds of thousands of times more light and heat than the Sun. They burn through their fuel at incredible speed, shining furiously bright, but only for a short time. And when they die, they go out with a spectacular explosion. Many of these monster stars are found in strange places, faraway galaxies like the Large Magellanic Cloud, a small irregular galaxy near our own. These galaxies have lower amounts of heavy elements like carbon, oxygen and iron, what astronomers call low metallicity. This makes it easier for stars to grow bigger before they begin to lose their mass. These galaxies are like cosmic nurseries where extreme stars are born, stars that challenge the laws of physics with their enormous power. But in space, being big comes with a price. The bigger a star is, the faster it lives. Its heart burns so hot and so fast that it quickly uses up all its fuel. While a smaller star like our Sun can live for around 10 billion years, the bigger stars only survive for a few million years. These aren't gentle old gods watching over the universe. They are fierce, blazing giants, beautiful and terrifying, living fast and dying young in the darkness of space. In the far corners of space, beyond the familiar swirl of our Milky Way, lie galaxies so strange and wild that they seem to break the rules of how stars are supposed to form. These aren't quiet, peaceful places. They're chaotic, raw, and bursting with energy, perfect homes for monsters of the cosmos. Some of the brightest and biggest stars ever discovered, like the enormous Stephenson 218 and UY Scuti, come from these bizarre galactic neighbourhoods, far from the calm lanes of our own galaxy. These massive stars don't just pop into existence out of nowhere. They are born in extreme environments, harsh, rare places that act like cosmic pressure cookers. Many of these stars come from satellite galaxies or galactic groups with strange chemical makeups, where furious waves of starbirth, called starbursts, are constantly shaking up the clouds of gas and dust. To truly grasp how terrifyingly powerful these gigantic stars can be, we need to first understand where they come from and how they grow. One key factor in the birth of these giants is something called metallicity, which in astronomy refers to how much of the gas contains elements heavier than hydrogen and helium. These heavier elements, which astronomers call metals, include things like carbon, oxygen and iron, materials created inside older stars and then scattered into space when those stars died. Here's the surprising part. The less of these metals a gas cloud has, the easier it is for it to collapse and form a massive star. That's because metals help gas clouds cool down by releasing heat, which makes them break up into many smaller stars. But in places with fewer metals, like certain regions in a nearby galaxy called the Large Magellanic Cloud, the gas clouds stay warmer and more intact. Instead of breaking into tiny pieces, the whole cloud can collapse into one or just a few very large stars. These metal-poor galaxies become star factories, not for tiny flickers of light, but for huge blazing titans. In such places, star clusters are born in great numbers, sometimes hundreds or even thousands of stars forming all at once. In the middle of this cosmic chaos, some lucky stars begin to suck up more gas than their neighbours. They grow fast, devouring their surroundings in a kind of cosmic cannibalism, where only the strongest survive and thrive. The first stars to form, especially those in the densest parts of a gas cloud, get the biggest helping of material. They hoard the cosmic fuel and become supergiants, hypergiants, and what astronomers sometimes call monster stars. But it's not just where a star forms, it's also how the gas cloud moves. If there's turbulence, wild, chaotic motion, or if the cloud spins just right, it can push material toward the centre with stunning speed. And when gravity wins over pressure, a single star can grow to be dozens or even hundreds of times more massive than our Sun before it even fully ignites. There's a strange cosmic irony in all this. While it's harder to form these enormous stars, once they exist, they dominate everything around them. Their powerful light and radiation can change the shape of nearby gas clouds. Sometimes they trigger the birth of new stars. Other times their energy is so intense that they stop star formation entirely, like a cosmic queen demanding all the attention and refusing to let anyone else shine. Here's one of the most fascinating things scientists have discovered. It may have been much easier for these colossal stars to form in the early days of the universe. Back then, the first galaxies were filled mostly with pure hydrogen and helium, no metals at all. This was the perfect setup for what astronomers call population 3 stars, the first generation of stars ever. These ancient giants might have been hundreds or even thousands of times heavier than the Sun. We've never seen them directly, but their descendants, like the modern Behemoth stars, might still be shining, far away, as echoes of that long-ago chaos. One of the best places to study this kind of extreme starbirth is a nearby dwarf galaxy, called the Large Magellanic Cloud, or LMC for short. If the Milky Way is like the capital city of our cosmic neighbourhood, the LMC is the wild frontier, a rough, energetic place full of surprises. Even though it's small, just about 1/10 the mass of the Milky Way, the LMC packs a powerful punch. Located around 163,000 light-years from Earth, It orbits our galaxy like a close companion, and despite its size, it's incredibly good at producing massive stars. In fact, it creates more high-mass stars per unit of gas than the Milky Way does. The LMC is like a galactic forge, glowing with fiery star nurseries and bright clouds of gas called nebulae. One of the most famous of these is 30 Doradus, better known as the Tarantula Nebula. It's one of the most active star-forming regions anywhere in our local galactic group. So what makes the LMC so special? It all comes down to chemistry and chaos. Its gas has a lower metallicity than the Milky Way, meaning it has fewer heavy elements. This keeps the gas warmer and less likely to break into small pieces, leading to fewer but much larger stars. The LMC doesn't go for balance, it goes for extremes. This makes it the perfect birthplace for giants like the Behemoth star. Hidden deep within the LMC and wrapped in a thick cloud of dust, this star is almost impossible to see, even with powerful infrared telescopes. But what we do know is jaw-dropping. It is over 1,500 times wider than our Sun and shines with a light 280,000 times brighter. And it's not just big, it's also slowly falling apart. The Behemoth star is losing its outer layers in a steady glowing breath, like a tired giant exhaling its life into space. Because it's so close, with less dust blocking the view, the LMC has become a cosmic laboratory where scientists study how stars live and die, especially the massive ones. Telescopes like the Hubble Space Telescope and the Very Large Telescope can look straight into its star clusters and nebulae, watching giants being born, living out their fiery lives, and collapsing into silence. Even more fascinating is the idea that the Milky Way's gravitational pull might be stirring up the gas in the LMC, sparking even more waves of star formation. Some scientists believe that billions of years from now, our two galaxies will collide in a spectacular cosmic dance. It would be like fireworks on a galactic scale, with stars flying out like glowing sparks. The LMC offers us a glimpse into what the universe was like in its younger, wilder days. Its strange structure, its metal-poor gas, and its furious star nurseries all reflect what early galaxies may have looked like. So when we study stars like the Behemoth star, we're not just learning about one giant, we're peeking into the ancient drama that shaped the cosmos itself. The Large Magellanic Cloud isn't just a small galaxy next door, it's a primordial furnace, a wild, beautiful reminder that in the universe, size isn't everything, but extremes make all the difference. A hypergiant star is one of the rarest and most extreme kinds of stars in the entire universe. These giants shine with incredible brightness, have massive sizes, and lose material from their outer layers at astonishing rates due to their powerful stellar winds, streams of gas blown away by their own intense radiation. In the language that astronomers use to classify stars called the MKK system, a hypergiant falls into luminosity class 0. But you don't often see this class 0 label written down in scientific papers. It's mostly used for very special types of stars, like yellow hypergiants, red supergiants, and blue supergiants that show strong glowing lines in their spectra, what scientists call emission spectra. More commonly, hypergiants are described with labels like IA0 or IA+, while red supergiants don't usually get those special classifications, even when they're massive. Why are astronomers so fascinated by hypergiants? Because these stars hold important clues to how stars are born, how they change over time, and how they eventually die, often in huge explosions called supernovae. Famous examples of hypergiants include the Pistol Star, a blue hypergiant that lies close to the centre of our galaxy. It's one of the brightest stars ever discovered. Rho Cassiopeiae, a yellow hypergiant that is so bright you can see it with your own eyes from Earth. And Mu Cephei, also known as Herschel's Garnet Star, which is one of the biggest and brightest stars ever observed. Back in the year 1956, two astronomers named Feast and Thackeray used the term supergiant, which was later changed to hypergiant, to describe stars that were brighter than an absolute magnitude of -7. That's extremely bright. Later, in the year 1971, another astronomer named Keenan suggested using the term hypergiant only for those supergiants that show a very wide, bright emission line in a part of their light spectrum called H-alpha. This feature hints at a very extended atmosphere and strong mass loss. Today, Keenan's rule is still the one most scientists use, which means that in some cases, a regular supergiant might actually shine brighter than a hypergiant of the same type. One way scientists can tell a star is a hypergiant is by looking at its spectral lines, the fingerprints of light that tell us what the star is made of. In hypergiants, these lines are usually stretched and shifted toward the red end of the spectrum, a feature called the P Cygni profile. But when it comes to the coolest hypergiants, those with lower surface temperatures, this method isn't very useful, so astronomers mostly rely on how bright the star is and how much material it is losing. Stars that start their lives with more than 25 times the mass of our Sun don't stay in the stable main sequence phase for very long. Instead, they quickly become blue supergiants, shining brightly while still quite hot. Then, without changing brightness much, they expand and cool into red supergiants. Later they shrink again, heat up, and might go back and forth between hot and cool phases in what scientists call blue loops. In the end, they usually explode as a supernova, or lose their outer layers and turn into a special kind of hot star called a Wolf-Rayet star. But if a star is born with more than 40 times the mass of the Sun, it's too powerful to ever settle into a red supergiant phase. These stars are so luminous that their outer layers can't stay stable and are blown away before the star gets a chance to cool down. The most massive stars of all, especially those that spin quickly and have more internal mixing, may skip all intermediate stages and become Wolf-Rayet stars directly. Hypergiants live at the very top of the Hertzsprung-Russell diagram, which is a chart astronomers use to compare stars by brightness and temperature. These hypergiants might be either freshly evolved massive stars that have just left the main sequence, or they might be older stars that have already gone through the red supergiant phase and lost much of their mass. Just looking at their brightness and temperature isn't enough to tell the difference. Young massive stars with lots of hydrogen left are usually more stable, while older stars that have burned most of their hydrogen and are filled with heavier elements become unstable. Their atmospheres become puffed up and harder to hold together due to high radiation pressure and weaker gravity. These unstable, massive stars near the Eddington limit, the point where radiation pressure nearly blows the star apart, are the ones we call hypergiants. Yellow hypergiants, in particular, are thought to be stars that have already passed through the red supergiant phase and have lost most of their hydrogen-rich outer layers. Some yellow supergiants are still on their way to becoming red supergiants, but that stage is short and rare. Because yellow hypergiants are in the post-red supergiant stage, they have an upper brightness limit of about 500,000 to 750,000 times the brightness of the Sun. Blue hypergiants, on the other hand, can be several million times brighter than the Sun. Most hypergiants don't shine with a steady light. Their brightness changes slightly because of chaotic processes happening deep inside them. However, in some zones of instability, especially where luminous blue variables, LBVs, and yellow hypergiants exist, these changes can be more dramatic. Hypergiants don't live very long. While stars like the Sun can survive for around 10 billion years, hypergiants last only a few million years. They are born in the largest, most crowded star-forming regions in space. Because they burn through their fuel so fast and die young, we haven't found very many of them, despite the fact that they are incredibly bright and can even be seen in nearby galaxies. Some stages in their lives, such as the LBV phase, might only last a few thousand years, which is like a blink of an eye in the vast history of the universe. Hypergiants are not just huge, they shine with an almost unbelievable brightness. As a star's mass grows larger, its brightness increases dramatically. In fact, hypergiants are often so luminous that they reach a point known as the Eddington limit. This is the critical balance point where the outward push of light and radiation from inside the star becomes strong enough to nearly equal the inward pull of gravity. If the radiation becomes just a little stronger than gravity, it could actually start to blow the outer layers of the star away. In simpler terms, imagine the star is trying to hold itself together with gravity, but the light it's producing is pushing outward with such force that it could start tearing the star apart. If the light pressure goes beyond this Eddington limit, the star would begin to lose mass in violent bursts, shedding huge amounts of material. These powerful outbursts stop the star from becoming even more luminous, acting like a kind of safety valve to prevent it from burning too brightly for too long. One of the best-known examples of this is Eta Carinae, a truly monstrous star that might be around 130 times more massive than our Sun. Its light shines with a power estimated to be 4 million times brighter than the Sun. Astronomers believe Eta Carinae has already gone beyond the Eddington limit at least once. This might have happened between the years 1840 and 1860, during a series of gigantic outbursts, where the star lost mass much faster than current science says should be possible through ordinary stellar winds. Usually stars lose material through winds powered by what's called line-driven radiation. That means atoms in the star's outer layers absorb light at specific wavelengths, helping to push material away. But hypergiants like Eta Carinae are so intense that they may also have continuum-driven winds, a more extreme kind of radiation pressure that doesn't need the presence of metal atoms like carbon or iron. This is important because many massive stars, especially very old ones or those born in the early universe, are metal poor, meaning they don't have many elements heavier than helium. This continuum radiation might explain how the very first stars in the universe, born right after the Big Bang, were able to lose mass and stay below a certain size, even though they had no metals at all. It could even be the reason why stars can only grow so massive before something stops them. Another idea scientists are exploring is that hypergiants might sometimes experience deep internal explosions. These would happen far below the surface, in the star's inner layers, where heat convection, the process of moving heat around, is not working properly. If the heat can't escape the way it's supposed to, the density of the material might flip, creating instability and possibly leading to a huge blast that throws parts of the star's outer layers into space. But this is still a theory, and hasn't been studied deeply yet. There's also a curious concept called a pseudo-photosphere. Normally, the photosphere is the visible surface of a star, the layer where its light escapes. But in some hypergiants, especially when powerful stellar winds are present, this visible surface might not be the real outer layer of the star. Instead, it could be a thick cloudy shell of wind that forms a fake surface. This wind-made surface would be much cooler than the hotter star underneath. Scientists think this might explain why some bright stars, like yellow hypergiants, appear cooler than expected. These stars might actually be luminous blue variables, LBVs, that have formed a pseudo-photosphere and just look cooler than they really are. Hypergiants are massive, evolved stars that shine with incredible brightness. On a diagram called the Hertzsprung-Russell diagram, which maps out different types of stars by their temperature and luminosity, hypergiants often overlap with other kinds of stars. It's sometimes hard to tell if these differences in classification mean the stars started out differently, are at different stages of life, or if we're just seeing them in different ways. While many theories agree on how these stars behave, the exact categories can get blurry. Most supergiants, which are already enormous stars, aren't as bright as hypergiants, though a few come close. What sets hypergiants apart is how wild and stormy they are. Their outer layers are often shedding mass, and they show strong hydrogen emissions in their light spectrum. Supergiants that started with less mass usually don't go back to a cooler red supergiant stage. Instead, they explode as supernovae or end up as white dwarfs, small, dense remnants. Luminous blue variables, LBVs, are a special class of very hot and bright stars that show sudden changes in their light spectrum. Most of the time, they exist in a quiet state, in a region where brighter stars are usually hotter. But sometimes they have huge eruptions and shift to a strange zone on the diagram where stars of all brightness levels settle, at about 8,000 degrees Kelvin, or roughly 13,940 degrees Fahrenheit. This area is near the unstable territory where yellow hypergiants are found. Scientists still aren't sure if yellow hypergiants ever manage to evolve into LBVs or go straight into exploding. Blue hypergiants live in the same area of the diagram as LBVs but don't always show the same behaviour. Some LBVs have hypergiant-like features some of the time, but not all astronomers agree on whether they should be considered true hypergiants. Some experts believe blue hypergiants might later turn into LBVs, or that LBVs could become blue hypergiants again. Others think some lower mass LBVs may be transitioning into or from cool hypergiants, or maybe they're something entirely different. Then there are the mysterious Wolf-Rayet stars. These are some of the hottest stars we know of, and they've already lost most of their outer layers. One specific group called WNL stars, which stands for late-type Wolf-Rayet stars, are a bit cooler and show nitrogen in their light. Some of these stars might be the stage hypergiants reach after losing enough mass. But there's a twist. Some hydrogen-rich WNL stars might actually be the ancestors of blue hypergiants or LBVs. A few related types, like OFF stars and WN9 stars, may be short-lived phases between massive main sequence stars and hypergiants. Even more fascinating is that some LBVs in their quiet phase have been seen showing WNL-like spectra, and some stars thought to be off-WNL types have suddenly changed, looking more like blue hypergiants. It turns out that rapid spinning in massive stars causes them to fling away their outer layers quickly, skipping the supergiant stage altogether and going straight into the Wolf-Rayet phase. Despite their strong light and heavy emissions, stars like Wolf-Rayet stars, cool/stars, off plus and off types are not officially considered hypergiants. They belong to their own special families, with unique spectral features that set them apart. Hypergiant stars are some of the rarest and most mysterious giants in the universe, and that makes them incredibly difficult to study. These stars are not just rare, they are unpredictable too. Many of them have constantly changing light signatures, known as spectra, which can make it hard for astronomers to understand exactly what's going on inside them. Because of this, scientists often place hypergiants into broad groups based on the general patterns they see in their light, rather than specific details. Some of the most fascinating hypergiants are part of a special group called luminous blue variables, or LBVs. These are unstable, massive stars that go through wild changes in brightness and behavior over time. In fact, some of them are only considered hypergiants during certain parts of their life cycles. Here are a few extraordinary examples. AG Carinae is a truly massive star located in the Carina constellation, far in the southern sky. It belongs to the LBV class and is in the middle of a dramatic transformation from an O-type star, a very hot and bright star, into a Wolf-Rayet star, which is a stripped-down, burning core nearing the end of its life. Eta Carinae, perhaps one of the most famous stars in our galaxy, also lives in the Carina constellation, specifically inside the breathtaking Carina Nebula, officially called NGC 3372. Eta Carinae is a true monster of a star. Its mass could be anywhere from 120 to 150 times greater than the Sun's, and it shines with a light that is about 4 to 5 million times brighter than our Sun. Because of its strange and extreme behavior, some scientists think it may be something even more exotic than a typical LBV. P Cygni, found in the northern constellation of Cygnus, is another key member of this group. It is so important that it serves as the prototype, or the textbook example, of what an LBV's light spectrum usually looks like. S Doradus, located in the large Magellanic Cloud, a nearby galaxy, in the southern constellation of Dorado, is another famous LBV. In fact, for a long time these stars were actually called as Doradus variables because of how well this star represents the group. The Pistol star, officially known as V4647 Sagittarii, lies close to the very centre of our Milky Way galaxy, in the constellation of Sagittarius. It is over 25 times more massive than our Sun, and blazes with the power of about 1.7 million suns. Scientists think it might be an LBV, but they haven't yet confirmed whether it changes brightness over time. Not all hypergiants are blue. Some come in other colours too. Yellow hypergiants usually have what's called a late A-type to early K-type spectrum, which means their surface temperatures are lower than blue stars but still very hot. When A-type hypergiants are especially bright, they're sometimes referred to as white hypergiants instead. There are also some cooler hypergiants, which show up as red or orange stars. Two of these likely exist in a set of newly discovered star groups called the scutum red supergiant clusters. One of these stars is named F15, and might be joined by F13 in a cluster called RSGC1. Another one, known as Star 49, is part of RSGC2. Some of these red or cool hypergiants belong to the K to M spectral types, which include the largest stars ever seen when measured by their radius. These stars can be truly gigantic. Some of them have radii between 1,000 and 2,000 times that of the Sun. That means if they replace the Sun in our solar system, they could stretch far beyond the orbit of Jupiter. Even though astronomers don't often label red supergiants with the special hypergiant class, the term red hypergiant is sometimes used to describe the most bloated and unstable among them. Red supergiants are some of the most gigantic stars we know, truly titans of the cosmos. These stellar giants belong to what astronomers call the supergiant class, officially known as Luminosity Class 1 in the Yerkes or Morgan-Keenan system. In terms of volume, red supergiants are the largest stars in the entire universe, even though they are not the most massive or the most brilliant in terms of energy output. Two of the most famous and brightest red supergiants are Betelgeuse, which sparkles in the constellation Orion, and Antares A, the glowing heart of the Scorpius constellation. These two are the only red supergiants visible with first magnitude brightness, meaning they shine as some of the brightest stars in our night sky. Stars are grouped into different categories based on how bright they are and how strong gravity is at their surface. Scientists use the patterns in a star's light, known as its spectrum, to figure this out. Certain lines in the spectrum tell us how tightly packed the star's material is. If the surface gravity is low, that means the star is big and puffy, and that usually means it's extremely luminous or bright. Using this method, stars are sorted into groups, or luminosity classes: supergiants, bright giants, giants, subgiants, and dwarfs, like our Sun, which is a main sequence star. Even within the first class, there are further divisions. A star can be a regular supergiant, a very bright one, or fall in between. In some rare cases, especially for the most extreme stars with very weak gravity and intense mass loss, astronomers might call them Class 0 or Ia+, marking them as hypergiants, the wildest of all stars. However, the term hypergiant is almost never used for red supergiants, except for a few very unstable examples like VY Canis Majoris and NML Cygni, sometimes called red hypergiants. The word red in red supergiant tells us that these stars are cool, at least compared to other stars. Most red supergiants belong to the M-type class, which includes the coolest stars, and a few are K-type, which are slightly warmer. But K-type supergiants are quite rare, as they don't stay in that stage for very long. Some of these K-type stars are even referred to as orange supergiants, for example Zeta Cephei, or yellow hypergiants, like the star HR 5171AA. Red supergiants have surface temperatures below 4,100 degrees Kelvin, which is cooler than the Sun, but they are so large that they still shine with incredible brightness. These stars can be several hundred times to even more than 1,000 times the size of our Sun in radius. However, a star doesn't have to be huge to be called a supergiant. What really matters is how bright it is compared to its temperature. For example, Alpha Herculis is a cool giant star with a radius between 264 and 303 times that of the Sun, yet it is not classified as a supergiant. Meanwhile, Epsilon Pegasi, a K2 supergiant, has a radius of only 185 times that of the Sun, yet it qualifies because of its brightness and other features. Despite being cooler than our Sun, red supergiants are tens of thousands or even hundreds of thousands of times more luminous, simply because of their enormous size. The biggest red supergiants are believed to reach a maximum size of about 1,500 times the Sun's radius. Beyond that point, a star would become so unstable that it simply couldn't hold itself together. This theoretical limit is known as the Hayashi limit. These stars are not born this big. They start out as massive hot stars with about 10 to 40 times the mass of our Sun. Over time, they swell into red supergiants as they burn through their fuel. But stars with more than about 40 solar masses do not become red supergiants. Instead, they go through different evolutionary paths, often staying hot and compact until the end. At the upper range of red supergiant size and brightness, these stars lose mass at astonishing rates, far faster than our Sun. In fact, they can blow off millions of times more material than the Sun every year. This fierce shedding of outer layers creates glowing clouds of gas and dust, nebulae, surrounding the star. By the time a red supergiant reaches the end of its life, it might have lost a huge fraction of its original mass, usually ending up with about 10 times the Sun's mass when its core finally collapses. Exactly how much mass remains depends on how fast the star spins and what elements it started with. Red supergiants are also variable stars, meaning their brightness changes over time. Most of them flicker and fade slightly, although not always in a regular pattern. Because of this, they are called irregular or semi-regular variables, and they even have their own subclasses: slow semi-regular variables and slow irregular variables. Sometimes these stars vary only a little, but a few can change brightness by as much as 4 magnitudes, which is a huge shift in visible light. Studies have shown that these brightness changes happen for a few reasons. Some red supergiants show many overlapping rhythms, caused by things like pulsations, massive stellar winds and surface disturbances. Others show changes due to large convection cells, giant bubbles of hot gas rising and falling on the star's surface. These are much fewer in number, but far larger than those found on the Sun, and can lead to brightness variations as the star spins. When scientists look at red supergiants through powerful instruments called spectroscopes, they see a complex pattern of absorption lines, dark fingerprints of different elements and molecules in the star's outer layers. These spectral features, especially metal lines and molecular bands like those from cyanogen, Cn, or calcium, CO2, help astronomers figure out a star's size and brightness class. Red supergiants are wonders of the universe, the slow-burning titans near the end of their lives. Though they're not the hottest or the heaviest, they are among the largest and most luminous objects in the cosmos, and one day, these giants will end their lives in spectacular supernova explosions, enriching space with the heavy elements needed to form new stars, planets, and maybe even life itself. Around red supergiant stars there is a cloud of gas and dust called circumstellar material, and this region often glows in a special way known as maser emission. Think of a maser like a cosmic laser, but instead of light, it emits intense microwaves. These emissions usually come from water vapour and silicon monoxide, but sometimes they also come from hydroxyl molecules, although this happens only in thin, specific layers around the star. Astronomers can use incredibly precise radio telescopes, like the Very Long Baseline Interferometry or the Very Long Baseline Array, to map these masers. This helps scientists study the shape and behaviour of the material around red supergiants in amazing detail. It also allows them to measure exactly how far away these stars are by using a method called parallax. So far, this technique has mostly been used on individual stars, but in the future, it could help us better understand the layout of our entire galaxy and find red supergiants that are hidden behind thick clouds of dust. Even though red supergiants have burned through all their hydrogen fuel deep in their cores, the outer layers of these stars still contain mostly hydrogen. However, just before they explode, they lose so much of their outer material that helium can become as common as hydrogen on the surface. In some extreme cases, theoretical models suggest that they could lose nearly all of their hydrogen, leaving helium as the most abundant surface element. When stars first evolve into red supergiants and leave the main part of their life, called the main sequence, they usually have more oxygen than carbon at their surface, and nitrogen is the least abundant of the three. This reflects the chemical mix they were born with. But as the star ages, deep layers of nuclear fusion products are stirred up to the surface. This process, known as dredge-up, depletes carbon and oxygen while increasing nitrogen, because the star has been fusing hydrogen into helium using a process called the CNO cycle. Red supergiants are slow spinners. They rotate very slowly, or sometimes barely at all. Even if a star spun quickly earlier in its life, the strong winds and mass loss slow it down drastically by the time it becomes a red supergiant. Some red supergiants, like Betelgeuse, do show a bit of rotation, and scientists think this might be due to interactions with a companion star in a binary system. Interestingly, even though the outer layers rotate slowly, the cores of these stars can still be spinning rapidly, creating a large difference between core and surface rotation speeds. Stars are often grouped by a classification called luminosity class, and red supergiants fall into one of these. But this system can mix very different types of stars into one group. Scientists prefer a more precise definition. A true red supergiant is a massive star that begins fusing helium in its core without forming a degenerate, extremely dense helium core, or undergoing a helium flash. These stars will always go on to fuse even heavier elements and eventually collapse in a spectacular explosion known as a supernova. Some less massive stars, those with lower mass than typical red supergiants, can still appear like supergiants based on their brightness. They might reach a luminosity of about 1,000 times that of our Sun while on a phase called the Asymptotic Giant Branch, AGB. But these stars are quite different. They have different chemical compositions, they pulsate in different ways, and they end their lives not with supernovae, but by shedding their outer layers and becoming white dwarfs surrounded by glowing shells called planetary nebulae. There is a special class of these AGB stars called super AGB stars. These stars have masses of about 7 to 9 times that of our Sun. They're right on the edge, massive enough to begin fusing carbon in their cores, but not quite able to reach the conditions that form an iron core. Some of them might still explode, producing a rare kind of supernova caused by a process known as electron capture. A rare group of bright, low-mass stars called RV Tauri variables, which lie on an unstable region of the star chart, also belong to the AGB or post-AGB category. They pulse in brightness in a distinctive semi-regular way. Red supergiants develop from main sequence stars that began life with a mass of between about 8 and 30 to 40 times that of the Sun. Stars more massive than this don't cool down enough to become red supergiants. Less massive stars go through a different path. They form dense helium cores, experience a helium flash, burn helium around a core of carbon and oxygen, then shed their outer layers and end up as white dwarfs. Interestingly, some AGB stars may temporarily shine as brightly as real red supergiants, reaching tens of thousands of times the Sun's brightness. And some super AGB stars, those in the 7 to 9 solar mass range, can even begin to fuse carbon and may end in unusual supernovae caused by the collapse of an oxygen neon core without ever building up iron. Main sequence stars with between 10 and 30 or 40 times the Sun's mass start out extremely hot. Their surface temperatures are between about 25,000 and 32,000 degrees Kelvin. These stars are classified as early B-type or very late O-type stars. They are already very bright, glowing with a power of between 10,000 and 100,000 times that of the Sun, thanks to a fast type of fusion called the CNO cycle. Inside, they are fully mixed by convection. But unlike the Sun, their outer layers are not convective. After spending about 5 to 20 million years burning hydrogen in their cores, these massive stars run out of fuel. They then begin to burn a shell of hydrogen around a helium core. This change causes them to expand and cool, turning into supergiants. Their brightness increases to about 3 times what it was, and helium becomes more abundant at the surface, up to about 40%, but heavier elements are still mostly unchanged. As they cool further, these stars often cross an unstable region known as the Cepheid instability strip. Some of the most massive may temporarily become yellow hypergiants. Eventually they cool into the red supergiant phase, reaching late K or M spectral types. During this time, helium fusion begins deep in the core, but it doesn't immediately affect the surface appearance. The star develops a huge convective zone reaching from the surface deep into the interior, which brings nitrogen and some heavier elements to the surface. Some red supergiants go through blue loops, temporary periods when they get hotter before cooling back into the red phase. These loops are caused by a mix of factors: mass, rotation, and the star's chemical composition. During a blue loop, the star's temperature can rise to around 10,000 degrees Kelvin. Blue loops are more likely when the helium core grows large compared to the rest of the star and leads to rapid mass loss. Within just 1 or 2 million years of becoming red supergiants, these stars run out of helium in their cores. They then begin to burn carbon and eventually fuse even heavier elements layer by layer. This continues until the core is made of iron, which cannot be fused to produce energy. At this point, the core collapses in a matter of seconds, triggering a supernova explosion. From the moment carbon fusion begins, the star has only a few thousand years left. In most cases, the collapse happens while the star is still a red supergiant. Its hydrogen-rich outer layers are blown off, producing a Type II supernova. The ejected hydrogen cools slowly, so the brightness of the explosion stays high for a long time before finally fading, a signature of Type IIp supernovae. The most luminous red supergiants, those with lots of heavy elements like the Sun, can lose most of their outer layers before the final explosion. These evolve into yellow hypergiants or luminous blue variables and explode as Type 2L supernovae. These still have hydrogen, but not enough to create the long-lasting brightness plateau. If the star has lost nearly all of its hydrogen, it may produce a rare Type 2b supernova. These start with a normal hydrogen spectrum, but the hydrogen lines fade quickly, making them look more like a Type Ib supernova. Astronomers have identified the stars that exploded in Type 2p supernova. They had surface temperatures between 3,500 and 4,400 degrees Kelvin, and luminosities between 10,000 and 300,000 times that of the Sun. These match predictions for lower mass red supergiants. A few stars have been seen just before Type 2L and Type 2b explosions. These stars had temperatures up to about 6,000 degrees Kelvin, and luminosities around 100,000 times that of the Sun. They seem to be slightly more massive red supergiants that were losing mass quickly. Interestingly, no one has yet observed the explosion of the most luminous red supergiants. Scientists believe these stars shed all their outer layers and become Wolf-Rayet stars, hot, stripped-down stars, before they finally explode. Red supergiants are giant stars that have reached an advanced stage in their life, but they don't stay in that phase for long. In fact, these stars are always quite young, no older than about 25 million years. That might sound like a long time to us, but in the life of a star, it's actually very short. Red supergiants are born from very massive stars, and those massive stars usually only form in big groups of stars called clusters. So we usually expect to find red supergiants hanging around places where lots of stars were born together. However, there's a twist. Because only the rare, really massive stars can become red supergiants, and because these giants burn through their fuel so fast, there are never many of them in one place at the same time. Even in a big cluster, you might only find a handful of red supergiants. For example, the massive star cluster known as Hodge 301, located in the famous Tarantula Nebula, has only 3 red supergiants. Before the 21st century, the largest number of red supergiants ever found in a single cluster was 5. That was in a cluster called NGC 7419. More often than not, these stars are found alone rather than in groups. For instance, the bright and famous red supergiant Betelgeuse shines alone in the Orion OB1 association, and Antares stands out in the Scorpio-Centaurus group. But things started to get more exciting in the year 2006. That's when astronomers discovered several huge star clusters near the base of one of our galaxy's spiral arms, called the Crux Scutum Arm. Each of these clusters held multiple red supergiants. One of them, called RSGC-1, has at least 12 red supergiants. Another, RSGC-2, also known as Stephenson-2, has at least 26. Then there's RSGC-3 and RSGC-4, also called Alicante-8, each with at least 8 red supergiants. Altogether, astronomers have confirmed the existence of 80 red supergiants in just a small patch of sky in the direction of these clusters. This remarkable collection of stars appears to be the result of a giant wave of star formation that happened about 10 to 20 million years ago near the centre of our galaxy, where the central bar of the Milky Way begins. Astronomers have also found more big star clusters on the opposite side of this galactic bar. However, none of them contain quite as many red supergiants as the clusters near the Crux Scutum Arm. Even though red supergiants are rare in the universe, they shine so brightly and can be so large that we can spot them from far away, even with just the naked eye. Some of these stars even change brightness over time, which makes them even more interesting to astronomers. A star named Mira was once believed to be a red supergiant, but scientists now know that it belongs to a different type of giant star known as an asymptotic giant branch star. Some red supergiants are even more extreme. They're so huge and so bright that they're called red hypergiants. These monsters of the cosmos can have radii that are more than 1,000 times larger than our Sun. In a major survey of the nearby Magellanic Clouds, 2 small galaxies that orbit our Milky Way, astronomers found about a dozen very bright M-class stars that were each more than 250,000 times as luminous as the Sun. These enormous stars had sizes starting from about 1,000 times the radius of our Sun and going even higher. A subgiant is a special kind of star that sits in between two more familiar types of stars. It shines more brightly than a typical main sequence star like our Sun, but it is not as bright or as large as a giant star. The word subgiant can mean two things. It refers to a specific group in the system used to classify stars by their brightness, and it also describes a particular stage in a star's life as it ages and changes. The name subgiant was first introduced back in the year 1930. It was used to describe stars in the G and early K spectral classes with absolute magnitudes between plus 2.5 and plus 4. These stars seem to fill a gap between the clear-cut examples of main sequence stars like the Sun and giant stars such as Aldebaran. Even though subgiants were not as common as the stars in the main sequence or the giant category, astronomers realized they were an important part of the bigger picture. Stars are sorted using a system called the Yerkes spectral classification, which uses letters and numbers to show how hot a star is, like a 5 or M1, and Roman numerals to show how bright a star is compared to others of the same temperature. In this system, luminosity class 4, the Roman numeral 4, is used for subgiants. These stars are positioned between class 5, main sequence stars, and class 3, giant stars. To figure out what class a star belongs to, astronomers don't just measure its brightness directly. Instead, they compare its light spectrum with those of other stars that are already well understood. Certain patterns in the spectrum, such as how deep or wide particular absorption lines are, can reveal how strong the gravity is at the star's surface, which helps determine whether it's a dwarf, subgiant or giant. Later studies showed that some stars originally labelled as subgiants were actually made up of two stars whose light blended together, or they were stars that varied in brightness over time. Even so, many of those early stars are still used today as the standard examples of subgiants. Interestingly, subgiant classifications are rare for the very hottest stars, O-type, and for stars cooler than spectral type K1. The subgiant branch is also the name of a phase in the lives of stars with low to medium mass, like the Sun. But not every star that looks like a subgiant is actually going through the subgiant phase, and vice versa. For example, stars like FK Commae Berenices and 31 Commae Berenices are probably in the subgiant evolutionary phase, even though they are sometimes labelled as giants. This can happen because a star's classification is influenced by more than just its brightness. It can also be affected by things like how fast the star spins, how much metal it contains, and even unusual chemical patterns. When a star like the Sun gets older, the amount of hydrogen in its core starts to run out. As this happens, the core contracts and heats up, making the hydrogen fusion around it go faster. This increases the star's brightness, and causes it to gradually move off the main sequence and begin the transformation into a subgiant. This shift shows up in a star chart called the Hertzsprung-Russell diagram as a widening of the main sequence band, because stars brighten as they age. Once the hydrogen in the core is completely used up, the core collapses and gets even hotter. Hydrogen then begins to fuse in a shell surrounding the core. This shell burning produces even more energy than the previous core burning phase. The outer layers of the star begin to swell and cool, and when the surface temperature drops to around 5,000 kelvins, the star becomes brighter again. This is when the star begins its journey up the red giant branch. The brief period of change between the main sequence and red giant stages is known as the subgiant phase. How this subgiant phase unfolds depends on the mass of the star. For example, stars with less than 40% the mass of the Sun, or 0.4 solar masses, are mostly made of convective material, meaning heat and particles flow through the star like boiling water. These stars keep fusing hydrogen throughout their entire volume and don't go through a subgiant stage at all. In fact, their life on the main sequence is so long, many times longer than the current age of the universe, that we have never seen one evolve beyond it. On the other hand, stars that are at least 40% as massive as the Sun develop a more complicated structure with a central core that doesn't convect. As soon as they run out of hydrogen in the core, the surrounding shell begins to fuse hydrogen instead. At this point, even though the star is now technically a subgiant, there's not much visible change on the surface. As this hydrogen shell keeps fusing, it produces helium, which slowly accumulates in the core. The energy from the shell fusion pushes outward, causing the outer layers of the star to expand. Depending on the star's mass, it can grow to between 2 and 10 times its original size. Despite this growth, the surface temperature doesn't change very much, so the star's spectral class stays nearly the same, especially for less massive stars in this range. However, because the surface area of the star becomes much larger, it radiates much more energy. For example, a star with a radius twice that of the Sun would give off 4 times as much energy, while a star with 10 times the Sun's radius would release 100 times more. This dramatic increase pushes the habitable zone, the region where liquid water could exist on a planet's surface, much farther out. During this time, the helium core is still not hot or heavy enough to start fusing helium. It stays in balance with the hydrogen-burning shell around it. As the hydrogen shell slowly burns outward and adds more helium to the core, the outer layers of the star continue to expand. The brightness of the star remains roughly steady during this stage, so in star clusters the subgiant branch appears as a short horizontal line filled with stars. Eventually, after somewhere between 1 and 8 billion years, the helium core becomes so massive that it can no longer support its own weight. The core becomes what scientists call degenerate, meaning it is supported by quantum forces rather than normal gas pressure. This triggers another round of changes. The temperature rises, the fusion shell burns even faster, the outer layers become unstable and convective, and the star grows brighter, without changing much in surface temperature. At this point, the star officially enters the red giant stage. Stars that are as massive as our Sun, or even larger, behave quite differently from smaller stars during their long life on the main sequence. While they are still fusing hydrogen in their cores, these stars have a central region that is churning and mixing due to convection. Over time, this central region builds up a large core of helium. Before they even run out of hydrogen in the entire convective zone, the helium core has already grown to take up a big part of the star's interior. Eventually, hydrogen fusion comes to a stop in the center of the star. With no more nuclear energy to hold it up, the core begins to shrink and heat up. This also causes the whole star to shrink and its temperature to rise. Strangely enough, even though fusion has stopped, the star actually shines more brightly during this phase. This process of heating and contraction can last for several million years. At some point, the temperature around the core becomes high enough to restart hydrogen fusion, not in the core itself, but in a shell that surrounds it. This reignited fusion in the shell causes the star's temperature and brightness to stop increasing. Instead, the outer layers of the star begin to swell, and the star cools down. This moment, when the star shifts from heating up to expanding and cooling, creates a noticeable kink in its path on the Hertzsprung-Russell diagram. Astronomers call this kink the end of the main sequence and the beginning of the subgiant phase. For stars with a mass less than about 2 times the mass of the Sun, their helium cores are still below a certain limit called the Schoenberg-Chandrasekhar limit. But once hydrogen shell fusion kicks in, the core quickly grows heavier and crosses that limit. More massive stars, on the other hand, already have cores that exceed this limit even before they leave the main sequence. The exact mass at which this change happens depends on 2 things: how many heavy elements, known as metals in astronomy, the star contains, this is called metallicity, and how far mixing from the convective core reaches out, which is known as overshooting. Stars with low metallicity can have cores that are unstable to convection, even if they aren't very massive. Overshooting can also cause the core to grow larger before hydrogen is completely used up. Once the helium core grows beyond the Schoenberg-Chandrasekhar limit, it cannot stay balanced with the hydrogen-burning shell anymore. The core contracts again, and the star's outer layers expand and cool. This expansion pulls energy from the center, causing the star's brightness to drop. When the outer parts of the star cool enough, they become opaque, and a new round of convection begins just above the fusion shell. The expansion then stops, and the star's brightness begins to rise once more. This moment is known as the beginning of the red giant phase. In stars with an original mass of around 1 to 2 times the mass of the Sun, the core may become a compact, degenerate ball of helium before this phase starts, just like in lower mass stars. This stage, where the core collapses and the outer layers expand, happens very quickly in cosmic terms, usually within just a few million years. During this time, the star cools dramatically, dropping from its main sequence temperature of around 6,000 to 30,000 degrees Kelvin to a cooler 5,000 degrees. Because this transition happens so fast, astronomers don't see many stars in this phase. This creates a noticeable gap in star charts known as the Hertzsprung gap, especially visible in star clusters that are between a few hundred million and a few billion years old. For stars with more than about 8 to 12 times the mass of the Sun, again depending on metallicity, things move even faster. These massive stars have large, hot convective cores powered by a process called the CNO cycle. For them, hydrogen shell fusion and even helium core fusion begin almost immediately after the hydrogen in the core runs out, leaving no time for a red giant phase. These stars, such as the early B-type main sequence stars, quickly pass through a short subgiant stage and become supergiants. Sometimes during this brief transition, they are classified as giant stars based on their spectra. In the case of extremely massive stars, like O-class main sequence stars, the whole transformation from main sequence to giant and then to supergiant happens across a very narrow range of temperature and brightness. In fact, some of these stars may become giants, or supergiants even before they have finished burning all their hydrogen. Because of how short and confusing this phase is, astronomers rarely label such stars as subgiants. For example, a measure of surface gravity, called log-G, is used to help classify these stars. O-type giants typically have a log-G value of around 3.6, while O-type dwarfs are closer to 3.9. In comparison, K-type stars like Aldebaran have much lower surface gravity, around 1.59, and smaller stars like Alpha Centauri b have much higher values, near 4.37. This wide range allows room for stars like Eta Cephei, a subgiant, to fall neatly in between with a log-G of about 3.47. Some of the most famous massive subgiants include Theta 2 Orionis A and the primary star of the Delta Cassini system, both of which are O-class stars with masses exceeding 20 times that of the Sun. In general, stars with fewer heavy elements, low metallicity, tend to be hotter and smaller than stars with more heavy elements, high metallicity. For subgiants, this makes things a bit more complex because age and the size of the helium core at the moment a star leaves the main sequence can vary. Stars with low metallicity tend to develop bigger helium cores before leaving the main sequence, so even stars with relatively low mass can show the distinctive hook at the start of the subgiant phase. For instance, a star with just one solar mass but very low metallicity, 0.001, which astronomers classify as an extreme population 2 star, can end its main sequence life with a helium core nearly twice as massive as that of a higher metallicity, 0.02, population 1 star. That low metallicity star will also be more than 1,000 degrees hotter and over twice as luminous at the start of its subgiant life. As it continues evolving, the temperature gap between the two types becomes smaller, but the low metallicity star remains larger and nearly 4 times brighter by the end of the subgiant phase. These trends hold for stars of many different masses. For example, the minimum mass a star needs to become a supergiant rather than a red giant is noticeably lower in environments with low metallicity. The Hertzsprung-Russell diagram, often called the HR diagram, is one of the most important tools that astronomers use to understand how stars live and evolve. It is a kind of graph, or scatterplot, that helps us see the life stages of stars based on 2 main features: their temperature, or spectral type, and their brightness, which can be shown as absolute magnitude or luminosity. On the horizontal axis, the x-axis, you'll find either the temperature of the stars or their spectral class, which tells us what kind of light they give off. On the vertical axis, the y-axis, you'll see how bright or luminous the stars are. When we plot lots of stars on this graph, a clear pattern appears. Most stars fall along a wide diagonal band called the main sequence. This is where stars spend most of their lifetimes, steadily burning hydrogen in their cores. But that's not all the diagram shows. You can also spot a good number of red giants, which are stars in a later stage of life, and white dwarfs, which are the final remains of stars like our Sun. Although white dwarfs are only seen if we observe very faint stars. Other areas of the diagram have far fewer stars since not all stars go through every possible stage. Subgiants are stars that have just started to leave the main sequence. They appear in a region above the main sequence, meaning they are brighter, but still below the red giants. On most HR diagrams, there aren't many subgiants, and that's because a star only remains in this phase for a relatively short time, much shorter than the long main sequence phase or the giant phase. So we don't catch many of them in this brief in-between stage. Among these subgiants, the hot ones, especially those belonging to spectral class B, look very similar to main sequence stars and are hard to tell apart. But the cooler subgiants are easier to spot, as they fill the wide space between the cooler end of the main sequence and the red giants. Interestingly, below about spectral type K3, this space is completely empty. No subgiants are found there at all. Astronomers can also plot the life paths of stars on the HR diagram. These paths, called evolutionary tracks, show how a star changes over time. For a star of a certain mass, you can trace its journey from the main sequence to the subgiant phase, and then up to the red giant branch. If you look at a group of stars that all formed at the same time, such as a star cluster, you can often see this subgiant path clearly. It appears as a band of stars between the point where the main sequence ends, called the turn-off point, and the beginning of the red giant branch. However, this subgiant branch only becomes visible in star clusters that are several billion years old, because only then have stars between 1 and 8 times the mass of the Sun had enough time to evolve off the main sequence. For example, globular clusters like Omega Centauri and older open clusters like Messier 67 are old enough to show a well-defined subgiant branch in their colour magnitude diagrams, which are similar to HR diagrams but based on colour and brightness. Omega Centauri is especially fascinating because it doesn't just show one subgiant branch, it shows several, and astronomers are still trying to figure out why. The best explanation so far is that Omega Centauri might contain multiple generations of stars, meaning stars of different ages all grouped together in the same cluster. Some subgiant stars that are more massive than the Sun go through an area of the HR diagram known as the Cepheid instability strip. This happens during their first crossing of the strip, although some stars may pass through this strip more than once during a later phase known as a blue loop. Stars with masses between about 2 and 3 times the mass of the Sun may become delta Scuti variables, which are stars that pulsate in brightness. One example of this kind of star is Beta Cassiopeiae. If the stars are even more massive, they may become classical Cepheid variables during their crossing of the instability strip. However, because these massive subgiant stars evolve very quickly, it is quite rare and difficult to catch them in this short phase. One star, S. Vulpeculae, was once thought to be a subgiant on its first crossing of the strip, but later studies showed it was actually on its second crossing. Astronomers have also found planets orbiting subgiant stars. Some examples of these planetary systems include Kappa Andromedae b, Kepler 36b and c, TOI 4603b, and HD 2246993b. Betelgeuse is a massive red supergiant star located in the famous constellation of Orion, which appears in the night sky as a mighty hunter. It is usually the 10th brightest star that we can see with our eyes from Earth, and within its own constellation, it comes second only to the brilliant blue-white star Rigel. One of Betelgeuse's most striking features is its deep reddish colour, making it stand out clearly in the sky. This huge star is what astronomers call a semi-regular variable star, which means its brightness doesn't stay constant. Instead, it changes over time in a somewhat predictable pattern. Betelgeuse's brightness, or apparent magnitude, swings between 0.0 and 1.6, with a main cycle that lasts around 400 days. This makes it the star with the widest brightness range among all the brightest stars in the sky. In fact, if you were observing in near-infrared light, Betelgeuse would appear as the very brightest star in the sky. The star's official scientific name is Alpha Orionis, which is based on the naming system introduced by the astronomer Johann Bayer in the early 17th century. It's often shortened to Alpha Ori. Now let's talk about size. Betelgeuse is an absolute giant. Its radius is somewhere between 640 and 764 times that of our Sun. To put that into perspective, if Betelgeuse were magically placed at the centre of our solar system, its outer surface would stretch far beyond the orbit of Mars. It would swallow up Mercury, Venus, Earth, and Mars entirely, and even reach past the asteroid belt. Estimates of Betelgeuse's mass vary, but most calculations suggest it is between just under 10 and a little over 20 times heavier than the Sun. Despite being relatively close in cosmic terms, its exact distance from Earth is surprisingly hard to pin down. Current best guesses place it somewhere between 400 and 600 light-years away, which is quite a wide margin for a star that's considered nearby. In terms of intrinsic brightness, or absolute magnitude, Betelgeuse scores around -6, a number that marks it as exceptionally bright. But it hasn't been shining for long. Betelgeuse is a young star, less than 10 million years old, but it has evolved very quickly because of its large mass. Stars like Betelgeuse burn through their fuel quickly and don't live long. Astronomers expect that Betelgeuse will end its life in a powerful explosion known as a supernova within the next 100,000 years. When this happens, it will light up the night sky as brightly as the half moon and remain that bright for more than 3 months. But don't worry, this cosmic event, though spectacular, won't pose any danger to life on Earth. Betelgeuse wasn't always where it is now. It was once part of the Orion OB1 Stellar Association, a group of young, hot stars that includes those in Orion's belt. At some point, Betelgeuse was flung out of its birthplace and became what astronomers call a runaway star. It's now racing through space at a speed of around 30 kilometers per second, fast enough to produce a bow shock, like the waves in front of a boat that stretches over 4 light-years wide. Back in the year 1920, Betelgeuse made history as the first star outside our solar system to have its photosphere, the visible surface, measured directly. Scientists have since found that Betelgeuse doesn't have a perfectly round shape. Its angular diameter, or apparent size in the sky, varies between 0.042 and 0.056 arcseconds. These variations are due to several reasons, including its irregular shape, surface darkening near the edges, pulsations and differences in how it looks in various wavelengths of light. Surrounding Betelgeuse is a huge and lopsided cloud of gas and dust, about 250 times larger than the star itself. This cloud was created as the star began shedding its outer layers into space. Among all the stars visible from Earth, only the Sun and another red giant called R Doradus appear larger in the sky than Betelgeuse when measured by angular size. Something fascinating happened starting in October of the year 2019. Betelgeuse began to dim noticeably. By the middle of February in the year 2020, its brightness had dropped dramatically, becoming about 3 times dimmer than normal. From magnitude 0.5, it fell to around 1.7. Then, as mysteriously as it dimmed, Betelgeuse began to brighten again. By April of the year 2023, it had returned to a more typical brightness, reaching a peak of 0.0 in visible light. Infrared observations taken over the past 50 years showed no big change in the star's overall energy output. This led astronomers to believe that the dimming wasn't caused by the star getting weaker, but rather by something blocking its light. A study using the Hubble Space Telescope revealed that the star had likely ejected a large amount of material from its surface. This material travelled millions of miles into space, cooled down, and turned into a dust cloud that temporarily dimmed the star's light. Betelgeuse's striking red colour has fascinated people for thousands of years. The ancient Greek astronomer Ptolemy described its hue as hyperkeiros, meaning something like orangey red. Later translations rendered this description into Latin as rubedo, meaning ruddiness. Interestingly, Chinese astronomers observing 3 centuries before Ptolemy recorded Betelgeuse as yellow instead of red. If that report was accurate, it might suggest that Betelgeuse passed through a yellow supergiant stage during that time, something modern scientists now consider possible. In southern Australia, Aboriginal communities have passed down stories for generations that describe Betelgeuse's changing brightness, showing that even ancient observers noticed its variable nature. The star's brightness changes were also recorded in the modern era. In the year 1836, the English astronomer Sir John Herschel began documenting Betelgeuse's brightness in his book Outlines of Astronomy. Between the years 1836 and 1840, he noticed dramatic changes in how bright the star looked. In October of 1837, and again in November of 1839, Betelgeuse even outshone Rigel. After a quiet spell of about 10 years, Herschel observed another brightening cycle that peaked in the year 1852. Later observations continued to note these fluctuations. For instance, the American Association of Variable Star Observers reported that Betelgeuse reached a maximum brightness of 0.2 in the years 1933 and 1942, while dropping to a minimum of 1.2 in 1927 and 1941. This variability may be the reason Johann Bayer labelled Betelgeuse with the alpha designation in his Uranometria star atlas of the year 1603, suggesting it rivaled or even outshone Rigel, which normally bears the beta label. In the Arctic, the Inuit people also considered Betelgeuse brighter than Rigel, partly because it sits higher in their sky and appears redder. They called it a Lurejuak, meaning large star. The first actual measurement of Betelgeuse's size came in the year 1920, when Albert Michelson and Francis Pease, with help from John Anderson, used a 6-metre interferometer attached to a 2.5-metre telescope at Mount Wilson Observatory. They found an angular diameter of 0.047 arcseconds, which, using a parallax value of 0.018 arcseconds, suggested a diameter of around 384 million kilometres, about 2.5 times the distance from the Earth to the Sun. However, because of effects like limb darkening and observational challenges, the accuracy of this measurement had some uncertainty. In the years that followed, particularly during the 1950s and 1960s, two important breakthroughs transformed how astronomers understood stars like Betelgeuse. First were the stratoscope balloon projects, which lifted telescopes high into Earth's atmosphere and captured incredibly detailed images of the Sun's surface. Second was the groundbreaking book Structure and Evolution of the Stars, published in the year 1958. Written by Princeton astronomers Martin Schwarzschild and Richard Herm, this book helped introduce the use of computers to build models of how stars evolve. These efforts confirm the presence of convective activity, similar to bubbling water, in the outer layers of stars like Betelgeuse. During the 1970s, astronomers witnessed some amazing breakthroughs in the way they observed stars. A major leap forward came with the work of French astronomer Antoine Laberry, who invented a technique called speckle interferometry. This clever method helped to reduce the blurriness caused by Earth's turbulent atmosphere, which had always made it difficult to get clear views of distant stars. Thanks to this innovation, ground-based telescopes could suddenly see with much sharper vision. It became possible to study the surface of stars like Betelgeuse, specifically its outer layer, known as the photosphere, in greater detail than ever before. Around the same time, astronomers also improved infrared telescopes placed on top of tall mountains like Mount Wilson in California, Mount Locke in Texas, and Mauna Kea in Hawaii. With these powerful tools, scientists started exploring the vast misty clouds of gas and dust that surround Betelgeuse. These clouds, known as circumstellar shells, appeared to contain enormous bubbles of gas. Astronomers believed these might have been formed by intense convection or boiling-like movements within the star, where hot gas rises and cooler gas sinks. But it wasn't until the late 1980s and early 1990s that researchers made even more dramatic discoveries. They began using a new technique called aperture masking interferometry. This involved placing a special mask with tiny holes over a telescope's opening, transforming it into a kind of makeshift interferometer, a tool that combines light from different points to create incredibly detailed images. Led by J.E. Baldwin and his team at the Cavendish Astrophysics Group, this method led to some of the most accurate measurements ever made of Betelgeuse's surface. It even revealed bright spots, hot areas on the star's surface that stood out against the cooler background. These were the first ever optical and infrared images of a star's surface other than our Sun, and they were first captured using ground-based telescopes like the Coast Interferometer. These bright patches or hot spots were exactly what the famous astronomer Martin Schwarzschild had predicted decades earlier. Huge convection cells dominating the surface of giant stars like Betelgeuse. Then, in the year 1995, the Hubble Space Telescope took things even further. Using its faint object camera, it captured an ultraviolet image of Betelgeuse that was sharper than anything seen from Earth. Since Earth's atmosphere blocks most ultraviolet light, this type of image can only be taken from space. In that Hubble image, scientists noticed a bright region in the southwest part of the star that was about 2000 degrees Kelvin hotter than the rest of the surface. Later, Hubble's Goddard high-resolution spectrograph showed that this hotspot might actually be one of the star's rotational poles. Based on this, scientists concluded that Betelgeuse's axis is tilted about 20 degrees from Earth's viewpoint, and its position angle is around 55 degrees from celestial north. By December of the year 2000, a new study measured Betelgeuse's diameter using the Infrared Spatial Interferometer, ISI. They found it to be about 55.2 milliseconds, which matched measurements taken by Albert Michelson almost 80 years earlier. Around that time, the Hipparcos mission estimated Betelgeuse's parallax at around 7.63 milliseconds, leading to an estimated radius of about 3.6 astronomical units, more than 3 times the distance between Earth and the Sun. But there was a surprise. In 2009, another study revealed that Betelgeuse had shrunk by about 15% since 1993, and it seemed to be shrinking even faster. Yet strangely, its brightness didn't change much. This made astronomers suspect that the shrinking might not be real. It could be due to shifting layers of gas in the star's extended outer atmosphere. Scientists also became deeply interested in the complex outer layers of Betelgeuse. Red supergiant stars like it play a crucial role in the galaxy by shedding matter that eventually helps form new stars and planets. But how they lose mass has remained a puzzle. Thanks to improved imaging techniques, astronomers began to close in on an answer. In July of 2009, the European Southern Observatory released spectacular images taken by the Very Large Telescope Interferometer. These images showed a huge plume of gas stretching 30 astronomical units, as far as the distance between the Sun and Neptune, away from Betelgeuse. This was just one of several such eruptions. In fact, astronomers have now found at least 6 layers of material around the star. Understanding how and why Betelgeuse is shedding so much gas may help explain how massive stars eventually explode as supernovae. Betelgeuse is also known as a pulsating semi-regular variable star. Its brightness goes up and down in cycles because its size and temperature are constantly changing. In one study, astronomers Richard Wassertonic, Edward Guinan, and Thomas Calderwood observed an unusually deep dimming and believed it was caused by a rare overlap of 2 cycles, a 5.9-year cycle and a 425-day cycle. By late 2019, other scientists began to wonder if this fading could be caused by something else, such as an eruption of gas or a thick dust cloud. Then, in early 2020, using the Hubble Space Telescope, astronomers found evidence that Betelgeuse had indeed blasted out a huge amount of superheated material. This material cooled and turned into a cloud of dust that blocked part of the star's light, about a quarter of its surface. Hubble had captured signs of this material moving through the star's outer layers during September, October, and November of 2019. By December, and into the first few months of 2020, many telescopes confirmed that Betelgeuse was much dimmer than usual. By January of 2020, Betelgeuse's brightness had dropped by a factor of about 2.5, going from magnitude 0.5 to 1.5. In February, it reached its faintest point in 25 years at magnitude plus 1.614, making it dimmer than Aldebaran and knocking it out of the list of the 10 brightest stars in the sky. This sparked widespread rumours that Betelgeuse might explode soon as a supernova. But astronomers reminded the public that this dramatic event probably won't happen for another 100,000 years. By mid-February of 2020, Betelgeuse had stopped fading and was even starting to brighten again. On February 22nd, the dimming seemed to end altogether. 2 days later, scientists found no major changes in the star's infrared emissions over the past 50 years, which suggested that the fading had nothing to do with the dying core. Instead, astronomers proposed that the dimming was likely caused by large dust grains forming close to the star, possibly from gas ejected in a prior outburst. Some also suspected giant star spots, cooler, darker patches on the surface, might be behind the dimming. Then, on March 31st, a rapid brightening was reported by several astronomers. Betelgeuse is usually hard to see from Earth between May and August, since it appears too close to the Sun in the sky. Just before its 2020 conjunction with the Sun, Betelgeuse had brightened to magnitude plus 0.4. But by June and July, the Stereo-A spacecraft detected a new dimming of about 0.5 magnitudes, which was unexpected. A new brightness peak was expected around August or September, but the fading hinted that another dip might arrive sooner than predicted. On August 30th of 2020, astronomers spotted a second dust cloud coming from Betelgeuse, linked to a smaller dimming that had occurred on August 3rd. By June of 2021, scientists thought the dust might have formed when a cool patch developed on Betelgeuse's surface. This idea was confirmed again by another research group in August. Then, in August of 2022, another study using Hubble confirmed that the dust likely came from a surface mass ejection, similar to explosions on the Sun, but far more powerful. This dimming may have been caused by the overlap of a 416-day cycle with a 2010-day cycle, creating what astronomers call a grand minimum, a very deep low point in brightness. This idea was first suggested decades ago by astronomer L. Goldberg. In April of 2023, astronomers reported that Betelgeuse had returned to peak brightness, reaching magnitude 0.0 visually and 0.1 in the V band, shining once again as one of the most dazzling stars in our night sky. Thanks to its deep orange-red glow and its prominent position in the constellation Orion, Betelgeuse is one of the easiest stars to spot with the naked eye. It stands out so clearly in the night sky that even casual stargazers can find it without the help of a telescope. Betelgeuse is one of the three bright stars that form the famous winter triangle, an imaginary triangle that helps people navigate the winter night sky. It also lies at the heart of another large star pattern called the winter hexagon, which connects several of the brightest stars visible during the colder months. Every year, in early January, Betelgeuse rises in the eastern sky just after sunset, marking the start of its most visible season. From about mid-September to mid-March, with the best viewing in mid-December, the star shines brightly in the night sky and can be seen from almost anywhere on Earth where people live, except for the most southern parts of Antarctica, south of 82 degrees latitude. By May in the northern hemisphere and June in the southern hemisphere, the red supergiant dips low in the western sky and can only be seen for a brief moment after sunset. A few months later, it reappears on the eastern horizon shortly before sunrise. However, during the in-between period, roughly June to July, especially around mid-June, Betelgeuse becomes invisible to the naked eye. It can only be seen using telescopes in daylight. An exception is in Antarctica, between 70 and 80 degrees south latitude, where it might still appear faintly in the north around midday twilight during the long polar night, when the sun never rises above the horizon. Betelgeuse is a variable star, meaning its brightness is not always the same. Its visual magnitude changes over time, ranging from 0.0 to about plus 1.6. At times, it can shine more brightly than the nearby star Rigel, making it the sixth brightest star in the night sky. On rare occasions, it even outshines Capella. But at its dimmest, Betelgeuse drops below stars like Deneb and Beta Crucis, and can become only the 20th brightest star in the sky. Astronomers have also discovered that Betelgeuse has up to 9 faint companions, stars that appear close to it in the sky. These companion stars lie at distances of about 1 to 4 arc-minutes away from Betelgeuse, and each one is dimmer than 10th magnitude, making them very hard to see without powerful telescopes. To measure how far stars are from Earth, astronomers use a technique called parallax. This is the apparent shift in a star's position in the sky when viewed from 2 different locations, in this case from opposite sides of Earth's orbit around the Sun. Even though the shift is tiny, often just a fraction of an arc-second, it can be used to calculate a star's distance. The first successful parallax measurement was done by Friedrich Bessel in the year 1838. Since then, scientists have tried to accurately measure the distance to Betelgeuse, but this has been surprisingly difficult. Knowing how far Betelgeuse is helps astronomers calculate many other important facts about it, such as how bright it really is, its luminosity, how big it is, its radius, how hot it is, its temperature, how old it might be, and how much mass it contains. Back in the year 1920, when astronomers first used interferometry, a technique to measure very small angles, to study the size of Betelgeuse, they assumed its parallax was 0.018 arcseconds. That gave a distance of about 56 parsecs, which equals around 180 light-years. But this estimate turned out to be too small, making all the other calculations, like its radius and brightness, completely inaccurate. Over the following decades, scientists proposed a wide range of possible distances for Betelgeuse, with some estimates as high as 400 parsecs, or about 1,300 light-years. Before the Hipparcos catalogue was published in the year 1997, there were already two somewhat conflicting measurements. One, made in 1991, suggested a parallax of 9.8 milliseconds, which placed the star at about 102 parsecs, or roughly 330 light-years away. Another estimate, published in 1993 from the Hipparcos Input Catalogue, gave a parallax of 5 milliseconds, translating to a distance of around 200 parsecs, or 650 light-years. Because these measurements were so different, astronomers ended up using a wide range of distances, which led to big variations in estimates of Betelgeuse's size, temperature, and brightness. When the full Hipparcos data was released in 1997, the measurement for Betelgeuse was 7.63 milliseconds, which suggested a distance of about 131 parsecs, or 427 light-years. This result had a smaller reported error than previous ones. However, later studies found that the uncertainties for variable stars like Betelgeuse had been underestimated. In the year 2007, a new and more accurate measurement was made, 6.55 milliseconds, with a smaller margin of error. This meant Betelgeuse was likely about 152 parsecs away, roughly 500 light-years, with an error of plus or minus 65 light-years. Then, in 2008, radio observations using the Very Large Array gave another result, a parallax of 5.07 milliseconds, suggesting a distance of about 197 parsecs, or 643 light-years, again with some uncertainty. The lead researcher, Edward Harper, explained that although the Hipparcos data was helpful, it still included unknown errors. So, they tried combining both sets of data, radio and optical, to balance out the mistakes and get a better estimate. Later observations using telescopes like ALMA and E. Merlin refined the parallax even more, giving a measurement of 4.51 milliseconds. This implied a distance of around 222 parsecs, which equals about 724 light-years, with some room for error on either side. In the year 2020, a new set of data came from the Solar Mass Ejection Imager, which is part of the Coriolis satellite. Along with 3 different modelling techniques, this produced a refined parallax of 5.95 milliseconds. This meant Betelgeuse was located at a distance of about 168 parsecs, or roughly 548 light-years. Based on this new measurement, astronomers concluded that Betelgeuse is likely 25% smaller and 25% closer to Earth than they had thought before. In the year 2022, a new study revealed something surprising about Betelgeuse. This massive star might actually be smaller and closer to Earth than scientists had thought before. The study was based on ancient records that showed Betelgeuse used to shine with a yellow colour about 1,000 years ago, but today it looks red. That colour change tells astronomers a lot. It suggests that Betelgeuse is not as massive as earlier estimates claimed, likely weighing around 14 times the mass of our Sun. This is significantly less than what was once believed. The study also pointed to a closer distance, about 125 parsecs, which is around 410 light-years away. That estimate fits well with earlier data collected by the Hipparcos satellite. However, the European Space Agency's current Gaia mission, designed to measure stellar distances with great precision, has trouble with stars that are too bright, such as Betelgeuse. The instruments on Gaia cannot handle stars brighter than about 6th magnitude. Because of this limitation, Betelgeuse did not appear in the mission's second data release from the year 2018, nor in the third release from the year 2022. Betelgeuse is classified as a semi-regular variable star. This means its brightness changes in a somewhat predictable pattern, but with many irregularities. Sometimes it follows cycles, but the brightness can vary a lot. The cycles can be different lengths, and there can even be times when no clear pattern is seen. It belongs to a special group called SRC stars. These are giant red stars that pulsate, with brightness changes of about 1 magnitude and cycles that last anywhere from a few dozen to several hundred days. Most of the time, Betelgeuse stays around magnitude plus 0.5 in brightness, but it can become as bright as magnitude 0.0 or fade as much as plus 1.6. It is listed in the General Catalogue of Variable Stars with a possible long-term cycle of about 2,335 days. Other, more detailed studies have found that Betelgeuse shows a main cycle of around 400 days, a shorter one of about 185 days, and a much longer secondary cycle of about 2,100 days. In February of the year 2020, astronomers recorded its faintest brightness in the V-band, plus 1.614. The changes in brightness are tied to the way Betelgeuse expands and contracts. These motions, called radial pulsations, are well understood. The periods lasting a few hundred days match the natural rhythm of the star's layers as they pulse in and out, either in the fundamental mode or in what's called the first overtone. Astronomers can detect these motions by observing the Doppler shift in the star's light, which tells them how fast parts of the star are moving toward or away from Earth. These shifts show that Betelgeuse is indeed expanding and shrinking, although changes in its temperature or light spectrum are not as clearly seen. Scientists have directly measured changes in Betelgeuse's diameter over time. They found that the 185-day pulses match the first overtone mode of pulsation. The ratio between this overtone and the longer period helps astronomers learn about what's going on inside the star and how old it might be. However, the long secondary cycle cannot be explained by simple radial pulsations. When astronomers use powerful instruments to examine Betelgeuse more closely, they sometimes see bright spots on its surface. These are likely massive convection cells, huge regions where hot gases rise and cool gases sink. Each of these cells might be nearly as wide as half the star and can emit 5 to 10% of Betelgeuse's total light. One idea is that the long secondary periods come from the motion of these cells combined with the slow rotation of the star. Other possible explanations include gravitational effects from a nearby companion star, magnetic activity in Betelgeuse's outer layers, or more complex non-radial pulsations such as gravity waves known as G-modes. Besides these regular pulsations, Betelgeuse also shows small, random variations in brightness. These are thought to be caused by granulation, small-scale turbulence on the star's surface, similar to what we see on the Sun, but much larger. On the 13th of December in the year 1920, Betelgeuse became the very first star beyond our solar system to have its size measured directly. Even though the technology of interferometry was very new at the time, the attempt worked. Using a technique that treated the star as a simple uniform disk, scientists estimated Betelgeuse's diameter at about 0.047 arcseconds. Taking into account limb darkening, the effect where the edges of the star look dimmer than the centre, they adjusted the measurement to around 0.055 arcseconds. Since then, other observations have measured Betelgeuse's angular diameter between about 0.042 and 0.069 arcseconds. When these angular sizes are combined with distance estimates ranging from 180 to 815 light-years, astronomers have calculated that Betelgeuse's radius might lie anywhere between 1.2 and 8.9 astronomical units, AU. To compare, Mars orbits the Sun at around 1.5 AU, the dwarf planet Ceres lies at about 2.7 AU, and Jupiter orbits at 5.5 AU. So if Betelgeuse replaced our Sun, its outer layer might extend beyond Jupiter's orbit, but would still fall short of Saturn's, which lies at about 9.5 AU. The size of a cool giant star like Betelgeuse is often reported using something called the Rossland radius. This is the distance from the star's centre to the point where the photosphere, the visible surface, becomes transparent enough that most of the star's light escapes. This value is based on the star's temperature and how much total energy it gives off. However, this differs from direct measurements, which must also account for limb darkening and the wavelength of light used for the observation. For example, a direct angular diameter of 55.6 milliseconds, MAS, could correspond to a Roslin diameter of 56.2 Ma. If there are clouds of dust or gas around the star, this might reduce the measured diameter to as low as 41.9 Ma. To solve these measurement challenges, astronomers have developed powerful tools. The original idea for astronomical interferometry was proposed by Hippolyte Fizeau in the year 1868. He suggested that looking at stars through two openings instead of one, similar to how human eyes create depth perception, could help measure the shape and brightness of stars. This idea led to the creation of the Michelson interferometer in the 1880s, and eventually to the successful measurement of Betelgeuse. Over the years, the technology improved rapidly. By using multiple openings, apertures, and combining the light through a mathematical method called Fourier analysis, astronomers could form highly detailed images. In the 1990s, this helped reveal the bright spots on Betelgeuse's surface. Other advances included adaptive optics, which correct for the blurring caused by Earth's atmosphere, space telescopes like Hipparcos, Hubble and Spitzer, and sophisticated instruments like AMBER, the Astronomical Multibeam Recombiner, which merges light from 3 telescopes to produce incredibly sharp images with millisecond resolution. Different wavelengths of light can give different sizes for Betelgeuse. In the visible range, the atmosphere scatters light more, making the star look slightly larger. In near-infrared, this effect is minimal, and astronomers can see the true edge of the photosphere. In the mid-infrared, the glow from the warm outer layers makes the star look bigger again. In the year 1996, Betelgeuse was measured as having a uniform disk size of 56.6 mass. In the year 2000, another team measured it as 54.7 mass. A slight adjustment for limb darkening gave a final value of about 55.2 mass. These values suggest a radius of around 5.6 AU, or 1,200 times the Sun's radius, assuming a distance of 197 parsecs. In 2004, near-infrared measurements found a smaller size of 43.33 ms. This helped explain why different wavelengths give different results. By 2009, measurements using the IOTA and VLTI interferometers strongly supported the idea that Betelgeuse is surrounded by dusty shells and a layer of molecules. These studies found diameters between 42.57 and 44.28 ms. A 2011 study confirmed these numbers, measuring a diameter of about 42.49 ms. That same year, the near-infrared diameter of 43.33 ms, paired with a distance of 152 parsecs, gave a physical size of about 3.4 AU, or roughly 730 times the radius of the Sun. In the year 2009, astronomers reported that Betelgeuse had shrunk in apparent size by 15% between the years 1993 and 2009. The 2008 measurement showed an angular size of 47 mas. The earlier measurement from 1993 was 56 mas. That meant a decrease in size of about 0.9 AU over 15 years. But this likely reflects changes only in the star's outer atmosphere, not the true photosphere, as measurements in other wavelengths showed an increase in size during that same period. Today, models usually place Betelgeuse's photospheric diameter at around 43 mad, with outer gas shells extending out to 50 or 60 mas. Assuming a distance of 197 parsecs, this translates to a diameter of about 887 times the radius of the Sun, with a margin of error of plus or minus 203 solar radii. Betelgeuse was once thought to be the star with the largest apparent size in the sky after the Sun. However, in the year 1997, astronomers measured another red giant, R Doradus, and found it had a diameter of 57 mass. Even though R Doradus is much closer to Earth, only about 200 light-years away, it appears larger in the sky. But because of its proximity, its actual size is only about 1/3 the size of Betelgeuse. Betelgeuse, one of the most famous stars in the night sky, is located far away from the path of the planets, the line known as the ecliptic. Because of this, the large planets like Jupiter or Saturn never pass directly in front of it, a rare event called an occultation. However, smaller objects like asteroids, which are more numerous and move in a wider variety of paths, can sometimes briefly pass in front of Betelgeuse from our point of view here on Earth. One such rare and fascinating event happened on the 2nd day of January in the year 2012. A faint asteroid called 2005 UW381, which shines at 19th magnitude, meaning it's incredibly dim and requires a telescope to see, partially blocked Betelgeuse's light. This event was only a partial occultation because the star's apparent size in the sky was actually larger than that of the asteroid. As a result, the brightness of Betelgeuse dipped just a tiny bit, by only about 0.01 magnitudes, barely noticeable even with precise instruments. Another intriguing event was predicted for the 12th day of December in the year 2023. This time, it was the 14th magnitude asteroid 319 Leona that was expected to pass in front of Betelgeuse at about 1:12 Universal Coordinated Time. Initially, scientists weren't sure if the asteroid would fully cover the star. The full occultation, if it happened, was expected to last only around 12 seconds and would be visible only along a very narrow path on Earth's surface. Because astronomers didn't yet have exact measurements of the asteroid's size and trajectory, the exact location of the viewing path was unknown at first. As scientists studied the data more closely, they refined their calculations. It turned out that the occultation, described as a dazzling ring of fire, would likely last around 5 seconds. The path of visibility, about 60 kilometers wide, would stretch across a long arc of the Earth, starting from Tajikistan, sweeping through Armenia, Turkey, Greece, Italy, Spain, across the Atlantic Ocean, then over Miami and the Florida Keys in the United States, and finally reaching parts of Mexico. This rare and accidental alignment offered astronomers a golden opportunity, not only to observe Betelgeuse dim momentarily, but also to gather valuable data about the asteroid Leona itself. Across Europe alone, about 80 amateur astronomers were coordinated by astrophysicist Miguel Montages and his team at the Paris Observatory to witness and study the event. Now let's turn to Betelgeuse itself, this massive glowing red supergiant in the constellation of Orion. It belongs to a class of stars known as M-type supergiants, with a designation of M1 to M2 Ab. The M means that the star is relatively cool and red in colour, while Ia Ab indicates that it's a luminous supergiant, not the brightest possible, but close. Its spectrum has been so reliable that since the year 1943, it has served as a reference point for classifying other stars. Measuring Betelgeuse's brightness, its luminosity, is tricky. That's because we still don't know its exact temperature, size, or distance. But back in the year 2012, astronomers estimated its luminosity to be about 126,000 times that of our Sun, assuming it lies about 200 parsecs away, which is around 650 light-years. Since the year 2001, measurements of Betelgeuse's surface temperature have ranged from 3,250 to 3,690 Kelvin. These values change due to natural pulsations in the star's atmosphere, almost like it's slowly breathing in and out. Betelgeuse is a very slow spinner. Its latest measured rotational speed was just 5.45 kilometers per second, which is much slower than that of Antares, another red supergiant, which spins at about 20 kilometers per second. How long does it take Betelgeuse to complete a full spin? Scientists estimate around 36 Earth years. But because the star is tilted at about 60 degrees to our line of sight, this spin is not directly visible. Even though Betelgeuse spins slowly, it may still have some magnetic activity in its huge outer layers. In the year 2004, astronomers using computer models suggested that large magnetic fields might form in the star's atmosphere and influence how it loses mass and blows off dust. Then, in the year 2010, a group of scientists used a special instrument called a spectropolarimeter at the Bernard-Lyot telescope in France. They discovered a weak magnetic field on the star's surface. This suggested that the powerful convection currents within Betelgeuse, similar to boiling water on a stove, could generate a small-scale magnetic dynamo, even without fast rotation. Unlike some stars, Betelgeuse doesn't have a visible companion orbiting it, so scientists cannot use gravitational measurements to figure out its mass. Instead, they use computer models. Modern estimates suggest that the star's mass lies somewhere between 9.5 and 21 times the mass of the Sun. Older estimates ranged even wider, from 5 to 30 solar masses. Based on how bright Betelgeuse is, and assuming it started with a luminosity between 90,000 and 150,000 times that of the Sun, it likely began its life with a mass between 15 and 20 solar masses. In the year 2011, astronomers introduced a new method for estimating Betelgeuse's mass. By analysing a detailed intensity profile using infrared interferometry, they came up with a current mass of about 11.6 solar masses, with possible values as low as 7.7 or as high as 16.6. Another analysis, using a statistical approach, suggested the current mass is probably between 16.5 and 19 solar masses, with an original mass between 18 and 21 solar masses. Another way to estimate the star's mass is by looking at where it sits on the colour magnitude diagram, which compares a star's colour and brightness. A study from the year 2022 looked at ancient records suggesting that Betelgeuse may have changed colour over the past few thousand years, from yellow or orange to deep red. This colour change implies a mass of around 14 solar masses, an age of about 14 million years, and a distance between 125 and 150 parsecs, or about 400 to 500 light-years. Betelgeuse's movement through space, its kinematics, is also complex and somewhat mysterious. Massive red stars like Betelgeuse, which began life with about 20 solar masses, typically only live for about 10 million years. If we trace its motion backward, Betelgeuse would have come from a location about 290 parsecs away from the galactic plane, a spot where stars usually don't form. Also, its current path does not appear to cross the known star-forming regions of Orion, like the 25 Orionis group or the much younger Orion Nebula cluster, also called Orion OB1d. Modern measurements using the Very Long Baseline Array show that Betelgeuse is between 389 and 414 parsecs from the Orion Nebula cluster. So, scientists now think Betelgeuse may have changed direction in the past, possibly due to a powerful nearby event like a supernova explosion. In January of the year 2013, the Herschel Space Observatory observed that the winds blowing off Betelgeuse were crashing into the gas and dust of the surrounding interstellar space. This shows just how powerful and far-reaching the star's influence is. Most astronomers now believe that Betelgeuse is a runaway star, one that was ejected from its original home. It likely formed about 10 to 12 million years ago as part of a high-mass multiple star system in a group known as Orion OB1a. Because it is so massive, it has aged quickly, growing into the red supergiant we see today. But not all scientists agree on its origins. In the year 2015, researchers H. Bowie and J. Alves suggested Betelgeuse might actually belong to a newly discovered group of stars called the Taurian OB Association. In the final stages of a massive star's life, especially stars like Betelgeuse, something fascinating happens. They begin to lose huge amounts of their mass. In fact, it's possible for a star like Betelgeuse to shed as much as one solar mass, which is the mass of our Sun, every 10,000 years. This steady outpouring of material creates a thick and ever-changing cloud of gas and dust around the star called the circumstellar environment. In the year 2009, scientists published a study emphasizing just how important this mass loss is. They called it the key to understanding not just how stars evolve, but also how the universe itself has changed since its earliest days. They even suggested that this process is deeply tied to the formation of planets and eventually the origin of life. Despite how crucial this is, scientists still do not fully understand how or why it happens. Back in the mid-20th century, a scientist named Martin Schwarzschild came up with a bold idea. He proposed that gigantic bubbles of hot gas called convection cells rise and fall within stars like Betelgeuse. He believed these turbulent motions could be behind the star's mass loss. More recent research has backed up this idea, but there's still a lot we don't know. Questions remain about how these convection cells are shaped, how dust forms in the outer layers, and what exactly triggers these stars to explode in spectacular Type II supernovae. In the year 2001, another scientist, Graham Harper, estimated that Betelgeuse was blowing out material through stellar winds at a rate of about 0.03 solar masses every 10,000 years. But more recent observations, especially those made since the year 2009, show that the star might not lose mass steadily. Instead, it might eject material in bursts or episodes, which makes it harder to know exactly how much mass has been lost overall. Interestingly, astronomers now think Betelgeuse doesn't just stay a red supergiant for the rest of its life. It might change phases again. At some point it may briefly become a yellow supergiant and then end its life either as a hot blue supergiant or as a Wolf-Rayet star, known for being very hot and stripped of its outer layers. Astronomers may be on the verge of understanding why this strange mass loss happens. They recently discovered a massive plume of gas stretching out from Betelgeuse, more than 6 times wider than the star itself. This plume suggests that the star isn't releasing gas evenly in all directions. Instead, it seems to be pouring out matter more in some directions than others. Normally, the surface of a star, called the photosphere, looks mostly round and symmetrical in infrared light. But Betelgeuse's outer layers don't match that shape. Using adaptive optics with a powerful telescope known as the Very Large Telescope, scientists saw lopsided patterns in the gas surrounding the star. 2 possible causes have been proposed, either giant convection cells bubbling beneath the surface or polar mass loss driven by the star's rotation. Digging deeper into the star's atmosphere using the AMBER instrument at the European Southern Observatory, scientists observed gas churning violently, with enormous bubbles rising and falling, some as large as the entire star. This violent movement is thought to be what created the huge gas plume observed by astronomer Pierre Cavella and his team. Betelgeuse's outer layers are much more complex than just a single photosphere. Scientists have now identified 6 additional parts of its atmosphere. Some of these regions are uneven, while others overlap each other in complex ways. Just above the surface, about 0.45 times the star's radius, or about 2 to 3 astronomical units, AU, lies the Emol sphere. This region contains molecules like water vapour and carbon monoxide, and has a temperature of around 1,500 kelvins, give or take 500. Water vapour was first detected in the star's light back in the 1960s, during the stratoscope missions, but this discovery was mostly ignored for decades. Newer studies suggest the Emol sphere may also contain silicon monoxide and aluminum oxide, both of which help form dust grains. Farther out is a cooler, uneven gas envelope, stretching 10 to 40 astronomical units from the surface. This envelope contains more oxygen and nitrogen than carbon, likely because material from deep inside Betelgeuse, processed by nuclear fusion reactions, has been brought to the surface and mixed into the atmosphere. In the year 1998, radio telescopes produced detailed images of Betelgeuse's atmosphere. These revealed that the gas temperature was about 3,450 kelvins, give or take 850, similar to the star's surface temperature but cooler than expected for gas in that region. The Very Large Array images also showed that this gas cools further as it moves away from the star. Surprisingly, this cooler gas turns out to be the most abundant part of Betelgeuse's atmosphere. As scientist Jeremy Lim explained, this discovery changed how astronomers think about red supergiant stars. Instead of the atmosphere expanding smoothly from hot gas near the surface, it now seems that giant convection cells launch gas upward, adding chaos to the star's surroundings. This is also the region where Cavella spotted a giant plume of material, rich in carbon and nitrogen, extending in the southwest direction as far as 6 times the star's radius. The chromosphere, a hotter outer layer, was directly imaged by the Hubble Space Telescope using ultraviolet light. It showed a bright area on the southwestern side of the star's disk. Back in 1996, scientists found that the chromosphere extended about 2.2 times the size of the visible star, or about 10 astronomical units, and had a temperature of up to 5,500 kelvins. Later, in 2004, a more advanced spectrometer on Hubble, called ESTIS, discovered warm plasma, hot ionized gas, stretching out to 1 arcsecond from the star. Since Betelgeuse is about 197 parsecs away, this means the chromosphere could extend as far as 200 astronomical units. This hot plasma overlaps with both the cooler gas envelope and the dusty outer layers, all swirling around the dying star. The first idea that Betelgeuse might have a surrounding dust shell came in 1977, when astronomers noticed that older stars often emit extra radiation from such dusty layers. Using a technique called heterodyne interferometry, they concluded that most of this radiation came from beyond 12 times the star's radius, or about 50 to 60 astronomical units, roughly the distance of the Kuiper belt in our solar system. In the 1990s, astronomers took more measurements at different wavelengths, but the results didn't always agree. Some studies placed the inner edge of the dust shell between 100 and 200 astronomical units, depending on assumptions about the star's size. These studies made it clear that the dusty surroundings are not stable. In 1994, it was reported that Betelgeuse produces dust in bursts lasting decades, followed by periods of calm. By 1997, scientists noticed the dust shell's shape had changed drastically in just 1 year. This suggested that bright spots on the star's surface were unevenly heating the surrounding dust. In 1984, a study claimed that an enormous asymmetric dust shell existed 1 parsec, or over 200,000 astronomical units, from the star, but this has not been confirmed. Another study from the same year proposed that 3 dust shells stretched as far as 4 light-years in one direction. If true, it would mean Betelgeuse has been shedding its outer layers as it moves through space. As for the 2 outer carbon monoxide shells, their exact sizes remain uncertain, but rough estimates suggest one extends between 1.5 and 4 arc-seconds, and the other reaches up to 7 arc-seconds. If we assume the radius of Betelgeuse is about 5.5 astronomical units, similar to Jupiter's orbit, then the inner shell would stretch from about 300 to 800 astronomical units, and the outer one could go as far as 1,400 astronomical units. To put that in perspective, our Sun's heliopause, the outer boundary of the solar wind, is around 100 astronomical units, so this outer shell would be nearly 14 times the size of our entire solar system. Betelgeuse, one of the most famous stars in the night sky, is a red supergiant nearing the end of its life. But it didn't always look like this. Long ago, Betelgeuse began its journey as a blazing hot blue-white star known as an O-type main sequence star. After it ran out of hydrogen fuel in its core, the power source that kept it shining for millions of years, it transformed into a blue supergiant. Eventually it cooled and expanded into its current form, a huge reddish-orange-red supergiant. What comes next for Betelgeuse is even more dramatic. One day its core will collapse under its own weight, setting off a massive explosion known as a supernova. What remains afterward will be a dense, compact object, possibly a neutron star or even a black hole. However, how exactly this process unfolds depends on the original features of the star, especially how massive it was when it was born, how fast it was spinning, and what elements it was made of. Since we didn't witness Betelgeuse's birth, scientists rely on computer models of stellar evolution to estimate what it was like in its early days. These models are based on its current size, brightness, chemical composition, and behaviour. Although there's still quite a bit of uncertainty, researchers believe Betelgeuse was originally between 10 and 25 times more massive than our Sun. More modern models narrow this range to somewhere between 15 and 20 solar masses. As for its composition, scientists estimate that Betelgeuse was made up of roughly 70% hydrogen, 28% helium, and about 2.4% heavier elements, a mix not too different from our Sun, but with slightly more metals. Its original rate of rotation is harder to pin down, but models that assume a slow to moderate spin match Betelgeuse's current characteristics best. In its early years as an O-type main sequence star, possibly something like a hot bright 09V type, Betelgeuse would have been a dazzling presence in its region of space. Now, how long would it have taken Betelgeuse to reach its current red supergiant phase? That depends on its mass and how fast it was spinning. A star with 15 times the mass of the Sun might take between 11.5 million and 15 million years to become a red supergiant. Heavier stars evolve faster. A 20 solar mass star that spins slowly might take only 8.1 million years, while one that spins rapidly could take about 9.3 million years. Based on this, astronomers estimate that Betelgeuse is now somewhere between 8 million and 8.5 million years old. But how long has it already been a red supergiant? That's harder to tell. Scientists try to estimate this by looking at the material Betelgeuse has ejected into space, and by measuring the abundance of heavier elements on its surface. Some models suggest Betelgeuse may have been in this phase for as little as 10,000 years, while others stretch this to as much as 140,000 years. The star seems to go through bursts of heavy mass loss, and is moving quickly through space, which makes exact estimates tricky. However, the most widely accepted figure is that Betelgeuse has been a red supergiant for around 40,000 years, and that it likely left the main sequence about 1 million years ago. During this red supergiant phase, Betelgeuse has already lost a significant amount of mass, but not too much. Models suggest that it has shed less than 1 solar mass, giving it a current estimated mass of about 19.4 to 19.7 solar masses. This is more than what some other measurements suggest, such as those based on how it pulsates, or how its brightness fades toward the edge of its disk, known as limb darkening. Any star with more than about 10 times the mass of the Sun is expected to end its life in a violent collapse. For stars with up to 15 solar masses, this usually means a Type 2p supernova, the kind that explodes after the star becomes a red supergiant. More massive stars, however, can lose their outer layers more quickly and may evolve into hotter stars, becoming yellow or blue supergiants, or even stripped down Wolf-Rayet stars before exploding. These different paths can lead to different types of supernova, such as Type 2L, Type 2b, or Type IBC. For example, models of rotating stars with 20 solar masses predict a strange type of supernova, like the famous SN 1987A from a blue supergiant. On the other hand, a similar non-rotating star would likely still explode as a Type 2p supernova from the red supergiant phase, just like Betelgeuse is expected to do. How much longer do we have before Betelgeuse explodes? That depends on how much time it's already spent as a red supergiant and how massive it truly is. A rotating 25 solar mass star might stay in this phase for around 300,000 years, while a non-rotating 15 solar mass star might last up to 1 million years. Based on the best models, Betelgeuse might only have less than 100,000 years left before it goes supernova, if it's a non-rotating 20 solar mass star. However, if it's rotating, or if it's less massive than that, it could stick around much longer. Astronomers believe that Betelgeuse was born in the Orion OB1 Association, a stellar nursery where several other massive stars have already exploded. In fact, 3 runaway stars, Mu Columbae, AE Aurigae, and 53 Arietis, were likely launched from this region by supernova explosions that occurred 2.2, 2.7, and 4.9 million years ago, respectively. When Betelgeuse does eventually explode, it will likely go out as a Type 2p supernova. This kind of explosion is incredibly powerful. It would release about 2 times 10 to the power of 46 joules in neutrinos, tiny, ghost-like particles, and another 2 times 10 to the power of 44 joules as the kinetic energy of the blast. From Earth, this event would be dazzling. At its brightest, Betelgeuse could shine with a magnitude between -8 and -12, bright enough to be seen in broad daylight and possibly rivaling the full moon, although probably not outshining it. After the explosion, its light would stay nearly constant for 2 to 3 months, thanks to the radioactive decay of cobalt formed during the blast. As the supernova's hydrogen shell cools and becomes more transparent, the light will fade, but it will remain a stunning celestial event unlike anything seen in recorded human history. In the year 1944, a German-American astronomer named Walter Baade came up with a way to group the different kinds of stars we see in our Milky Way galaxy. But Baade wasn't the very first to think about this. In fact, he mentioned in his paper that the idea had originally come from a Dutch astronomer named Jan Oort, all the way back in the year 1926. Baade noticed something very interesting. Stars that looked blue were usually found along the Milky Way's spiral arms, those curved arms that twist out from the centre of the galaxy like a giant pinwheel. On the other hand, yellowish stars were more commonly found near the thick central bulge of the galaxy and inside ancient clusters of stars called globular clusters. He divided the stars into 2 major groups, Population 1 and Population 2. Later, in the year 1978, scientists added a third group, Population 3, which is thought to be made of the very first stars that ever existed, although we've never seen one directly. What made these groups different was more than just their colour or where they were located. Scientists later found that these types of stars had very different light patterns, known as stellar spectra, basically fingerprints of what elements the stars are made of. These differences helped astronomers understand how stars form, how old they are, how they move, and even how galaxies like our own have changed over time. One of the biggest differences between these groups is their metal content. In astronomy, the word metal is used in a special way. It includes any element heavier than helium, such as oxygen, carbon, and iron, even though these aren't metals in everyday life. Here's the rule: the fewer metals a star has, the older it likely is. Population 3 stars were the very first stars to form in the universe, and they had almost no metals at all. Population 2 stars are also very old, with only small amounts of metals. Population 1 stars, like our Sun, are much younger and have the highest metal content. The Sun, for example, is a population 1 star with about 1.4% of its mass made up of metals. By studying the light from stars, scientists found that older stars always have fewer heavy elements than younger stars. This tells us something big: metals built up in the universe over time as generations of stars were born, lived, and died. This process is called stellar nucleosynthesis, which means stars create new elements inside them through nuclear reactions. According to our current models of how the universe began, almost all the matter created in the Big Bang was made of hydrogen, about 75%, and helium, about 25%, with just tiny traces of other light elements like lithium and beryllium. After the universe cooled down, the very first stars, population 3 stars, were born. These stars had no heavy elements at all, which may have made them behave very differently from modern stars. Scientists believe these first stars were huge, possibly hundreds of times more massive than the Sun. Because of their size, they lived very fast and died young. When they died, many of these massive stars exploded in extremely powerful pair instability supernovae, a rare and energetic kind of explosion. These explosions scattered the first heavy elements, like carbon, oxygen, and iron, into space. These metals then became part of the gas clouds that would later form new generations of stars. Because population 3 stars were so massive and burned out so quickly, scientists believe we can no longer see them in our galaxy today. However, we might catch glimpses of their light in very faraway galaxies from the early days of the universe. Interestingly, astronomers have discovered an extremely metal-poor star, slightly smaller than the Sun, that orbits in a binary system in the spiral arms of the Milky Way. This discovery gives hope that stars from the very early universe might still exist and be found. Some of the largest early stars didn't explode. Instead, they may have collapsed directly into black holes through a process called photodisintegration, where the star breaks apart from within. Some of the matter might have escaped during this process as powerful, high-speed jets of gas and radiation, helping to spread metals even farther into the universe. The oldest stars we've actually seen, population 2 stars, have very low metal levels but not zero. These stars formed from gas that had already been enriched by population 3 stars. As these population 2 stars aged and died, they released even more metals into the surrounding space through supernova explosions and glowing clouds called planetary nebulae. The next generation of stars, population 1, formed from this metal-rich gas and thus have the highest metal content. These include stars like our Sun. These younger stars are usually found in the spiral arms of galaxies and tend to orbit the centre of the galaxy in smooth, nearly circular paths. Population 1 stars were once thought to be more likely to form planets because of their higher metal content. Metals are the building blocks of rocky planets. But recent observations from the Kepler Space Telescope have shown that small planets can form around stars with both high and low metal content. However, giant planets, like Jupiter, still seem more common around stars with lots of metals. Between population 1 and population 2, stars lies another group called the intermediate disk population, which shares characteristics of both groups. Population 2 stars, which have low metal content, are found mostly in the galactic halo and the central bulge of the Milky Way. These stars are especially common in globular clusters, which are tight balls of very old stars. Even though population 2 stars don't have many metals, they often have more of certain lighter elements called alpha elements, like oxygen and neon, when compared to iron. Scientists believe this is because Type 2 supernova, which make alpha elements, were more common in those early times, while Type Ia supernova, which make more iron, became common later. Now, population 3 stars are still just a theory. No one has seen one directly. The idea was first suggested by astronomer Neville J. Wolfe in the year 1965. These stars were probably incredibly massive, hot, and bright, made entirely of hydrogen and helium with little or no metals, except maybe if they picked up some material from nearby supernovae. They may have started the process of creating the elements needed to build planets, and even life itself. Although we haven't seen them directly, scientists believe they once existed because they explain how the universe became filled with heavy elements. Some clues come from the light of distant galaxies and quasars. For example, one very distant galaxy observed by the European Southern Observatory, called Cosmos Redshift 7, may have contained a pocket of population 3 stars around 800 million years after the Big Bang. It also had some redder, older population 2 stars. Some scientists even think there might have been 2 generations of population 3 stars, one group of massive stars that lived very briefly, and a second group that formed slightly later. There's still debate about whether the first stars were all supermassive or if smaller ones also existed. Some early theories suggested these stars could have been as big as 1,000 times the mass of the Sun and might have lived only 2 to 5 million years. Other theories suggest that the first stars may have formed in groups, with one big star surrounded by several smaller ones. If any of the smaller ones were ejected early, they might still survive today, perhaps even in our own galaxy. Some stars, like the very metal-poor He0 107 to 5240, may have been formed from the material left behind by population 3 stars. Based on the data, those early stars might have had masses between 20 and 130 times the mass of the Sun. Interestingly, studies of globular clusters in elliptical galaxies suggest that pair instability supernovae played a major role in their chemical makeup. That might be why we haven't seen any stars with 0 metal content. None of the small population 3 stars seem to have survived. Some theories even suggested that low-mass zero-metal stars like red dwarfs or brown dwarfs could be hiding in the universe and might be part of dark matter. But despite searches using gravitational lensing techniques, none have been found. Population 3 stars may also have formed the first black holes in the universe. These weren't the massive black holes we sometimes hear about, but smaller ones. If they managed to grow large enough, they could have become quasi-stars, another type of mysterious object that may have existed before heavier elements filled the universe. One of the major goals of NASA's James Webb Space Telescope is to try to find these elusive population 3 stars. On December 8, 2022, astronomers announced that they might have finally caught a glimpse of population 3 stars in a distant galaxy called RxJ 2129 to Z8 HE2. If confirmed, it would be one of the biggest discoveries in modern astronomy, allowing us to look back in time and see the very first lights that ever shone in the universe. The life of a star is an incredible and dramatic journey that unfolds slowly across the vast ocean of time. This process, known as stellar evolution, describes how a star forms, changes, and eventually dies. A star's path through life depends almost entirely on how massive it is. The largest and heaviest stars burn brightly but live fast, often lasting only a few million years. In contrast, the smallest and lightest stars may shine steadily for trillions of years, outliving the universe itself, which, according to current estimates, is only about 14 billion years old. All stars begin their lives inside enormous dark clouds of gas and dust called nebulae, also known as giant molecular clouds. These clouds can stretch across 100 light-years and hold up to 6 million times the mass of our Sun. Over time, gravity pulls parts of these clouds inward. As the gas collapses, it breaks into smaller fragments. Inside each of these fragments, the gas gets squeezed tighter and heats up, turning into a glowing ball called a protostar. These protostars are the seeds of future stars. They are surrounded by dust and gas and are best observed using infrared telescopes, like NASA's Wide Field Infrared Survey Explorer, often called WISE. As a protostar grows by pulling in more gas and dust, it eventually reaches a balance and becomes a main sequence star, a stable, long-lasting phase where it shines by fusing hydrogen atoms into helium in its core. This nuclear fusion produces enormous amounts of energy, which is what makes stars shine. The type of fusion and how long it continues depends on the star's mass. For instance, if a star is about the same size as the Sun, what astronomers call one solar mass, it will burn hydrogen at its core for around 10 billion years. But much smaller stars like red dwarfs burn hydrogen so slowly that they could live for hundreds of billions or even trillions of years. On the other hand, giant stars that are many times heavier than the Sun can burn through their fuel in just a few million years. Once the hydrogen in the core is mostly used up, a star's life enters a new phase. In stars like the Sun, hydrogen fusion continues in a shell around the now helium-rich core. This causes the outer layers of the star to expand, and the star becomes a red giant. Eventually, these stars start fusing helium in their cores, and heavier stars can even go on to fuse elements like carbon, oxygen, and beyond in a series of onion-like shells. The end of a star's life depends again on its mass. A star like the Sun, when it runs out of fuel, sheds its outer layers, creating a glowing shell of gas called a planetary nebula, while its core shrinks into a small, incredibly dense object known as a white dwarf. These white dwarfs no longer produce energy, but they remain hot and slowly cool down over billions of years. Heavier stars, those with around 10 times the mass of the Sun or more, face a more violent ending. When they run out of fuel, their iron-filled cores collapse in an instant, triggering a colossal explosion called a supernova. What's left behind after this cataclysm is either a neutron star, which is incredibly dense and compact, or, if the original star was massive enough, a black hole, a region of space so dense that not even light can escape it. Very small protostars, those with less than about 8% of the Sun's mass, never become true stars. They do not get hot enough to ignite hydrogen fusion in their cores. These are known as brown dwarfs. Some of them are large enough to briefly fuse deuterium, a heavier form of hydrogen, but they never shine as brightly as full-fledged stars. Instead, they glow faintly and slowly cool off over hundreds of millions of years. Even smaller objects, those less massive than about 13 times the mass of Jupiter, are called sub-brown dwarfs, unless they orbit a star, in which case they are considered planets. Inside molecular clouds, long strands of dense gas known as filaments often appear. These filaments break up into smaller, tightly packed clumps of matter called gravitational cores, which are the direct ancestors of new stars. Sometimes, within a single filament, astronomers have found regular chains of dense cores, evenly spaced and occasionally containing pairs of protostars that shoot out jets of gas as they grow. As a protostar continues to grow and heat up, its central temperature eventually reaches about 10 million degrees Kelvin. At this point, hydrogen fusion begins through a series of reactions. For small to mid-sized stars, this is usually the proton-proton chain reaction. In slightly larger stars, those just a bit more massive than the Sun, another fusion method known as the carbon-nitrogen-oxygen cycle starts to play a bigger role. Fusion creates a powerful outward pressure that balances the pull of gravity, allowing the star to stay stable. This moment marks the beginning of the main sequence phase, which is the longest and most steady part of a star's life. Every star on the Hertzsprung-Russell diagram, a special chart used by astronomers, occupies a unique spot on the main sequence depending on how massive and hot it is. Tiny, cool red dwarfs live the longest. Massive hot blue stars, known as O-type stars, live fast and die young, sometimes after only a few million years. Stars like our Sun, called yellow dwarfs, spend about 10 billion years in this phase, and scientists believe the Sun is currently halfway through its main sequence life. As stars form, they can also develop disks of gas and dust spinning around them. These protoplanetary disks are where planets may eventually form, giving rise to complete planetary systems like our own solar system. As time passes, a star eventually uses up all the hydrogen fuel in its core, the very material that powers it through nuclear fusion. When this happens, the star can no longer stay stable as it once did on the main sequence of its life. During the main sequence stage, hydrogen atoms fuse into helium, producing energy that pushes outward and balances the inward pull of gravity. But once the hydrogen in the core runs out, that balance is lost. Without that outward pressure from fusion, gravity takes over. The core begins to shrink and grow hotter. One of two things can happen next, depending on how massive the star is. If it's not very massive, the core might stop collapsing when it gets so tightly packed that a strange quantum force called electron degeneracy pressure pushes back against gravity. If the star is more massive, then the core may become hot enough, about 100 million Kelvin, to start fusing helium instead. Whether electron degeneracy or helium fusion kicks in first depends entirely on the star's original mass. Now, here's the tricky part. For the smallest stars, we've never actually seen what happens when they stop making energy through fusion. That's because the universe itself is only about 13.8 billion years old, and these tiny stars live far, far longer than that, sometimes by many orders of magnitude. So their full life stories haven't had time to play out yet. According to current models, a red dwarf star with a mass of about 1/10, the mass of the Sun, could shine steadily for anywhere between 6 and 12 trillion years. That's 6,000 to 12,000 billion years. During this time, the star will slowly grow brighter and hotter. After that, it could take hundreds of billions of years more to finally shrink into a white dwarf. These tiny stars are unique. They won't puff up into red giants like larger stars. Instead, because they are completely stirred up by convection, they will keep burning hydrogen evenly until almost the entire star turns into helium. Stars that are a little heavier do become red giants. However, some of them aren't heavy enough to fuse helium in their cores, so after they expand and shine as red giants for a while, they don't climb to the brightest point of the red giant stage. Instead, they quietly fade and shrink down to become white dwarfs without going through the dramatic helium fusion phase. This slow exit is similar to stars on the post-asymptotic giant branch, just not as bright. But there's a turning point. Stars that start out with about 6/10 the mass of the Sun or more, what we might call mid-sized stars, can get hot enough to start fusing helium in their cores. These stars go through more complex stages of life after leaving the red giant phase. Stars with masses between about 6/10 and 10 times the Sun's mass become red giants, enormous stars that no longer belong to the main sequence. These glowing giants usually fall into the K or M spectral classes, meaning they shine with a reddish or orange hue. On the Hertzsprung-Russell diagram, which maps out stars by their brightness and temperature, red giants sit along the right edge. Famous examples include Aldebaran in the constellation Taurus and Arcturus in Boötes. These mid-sized stars pass through two red giant phases. In the first, called the red giant branch, they have helium cores that don't yet fuse, and hydrogen burns in a shell around the core. Later, in the asymptotic giant branch, their cores are made of carbon and fusion happens in two shells, one burning helium and the other hydrogen. In between these phases, stars spend some time on the horizontal branch where they burn helium in the core. Many stars here cluster into what's called the red clump. They shine steadily as cool K-type giants. When a star leaves the main sequence and its core runs out of hydrogen, fusion continues in a shell around the core. The shell keeps adding helium to the core, making it grow in mass. This stage can last anywhere from a few million to 1 or 2 billion years, depending on the mass of the helium core. During this time, the star grows in size and cools down a bit, but its brightness stays similar, or just a bit lower than it was before. Eventually something changes. In stars about the size of the Sun, the core becomes degenerate. It stops behaving like normal gas and is held up by quantum forces. In more massive stars, the outer layers grow cooler and thicker, making it harder for heat to escape. Both of these changes cause the hydrogen-burning shell to heat up and brighten, making the whole star swell up and rise onto the red giant branch. As the outer layers expand, they become full of convection, hot gas bubbling up and mixing with cooler gas. This mixing pulls fusion products from deep inside the star all the way to the surface. For most stars, this is the first time the materials created by fusion show up on the outside. Though the changes are subtle, scientists can detect them by studying the light from these stars. For example, they can see altered ratios of carbon and nitrogen and differences in the isotopes of hydrogen and helium, especially from the CNO cycle. On the red giant branch, the helium core keeps growing. Since it's not in balance with the rest of the star, it heats up even more. That makes the hydrogen shell burn faster, increasing the star's brightness as it climbs to the tip of the red giant branch. Stars with degenerate helium cores all reach this tip with about the same mass and brightness. In more massive stars, the core might get hot enough to ignite helium fusion even before reaching the tip. For stars with helium cores between about 6/10 and 2 times the mass of the Sun, which are mostly supported by electron degeneracy pressure, something explosive happens, a helium flash. This ignition happens in just a few days. In heavier stars, the core isn't degenerate, so helium fusion begins smoothly over time without any flash. During a helium flash, the power released is incredible, around 100 million times the Sun's brightness for a few days, and for a brief moment it may spike up to 100 billion times the Sun's brightness, equal to the entire Milky Way galaxy. But this burst of energy doesn't reach the surface of the star. It's used up to expand the tightly packed core, so we can't actually see it from the outside. As the core expands, it cools, and hydrogen fusion slows down. The whole star contracts, though not all the way back to its original size. It settles into a new stable phase and moves to the horizontal branch on the Hertzsprung-Russell diagram. Its radius shrinks, but its surface temperature rises. Stars that go through a helium flash move to the cooler end of the horizontal branch and shine as red clump stars, hotter and dimmer than red giants. More massive stars with larger helium cores slide toward hotter parts of the branch. Some of them become unstable and start to pulse rhythmically, forming RR Lyrae variables. Others grow even hotter and may appear as part of the blue tail or blue hook. The exact appearance and structure of the horizontal branch in a star cluster depend on things like the star's chemical makeup, its age, and how much helium it has. Scientists are still working out the fine details through theoretical models. Once a star has used up all the helium in its core, it doesn't stop shining right away. Instead, it keeps burning both hydrogen and helium in layers or shells that surround a hot and dense center made mostly of carbon and oxygen. This next stage of the star's life follows a path on the Hertzsprung-Russell diagram called the Asymptotic giant branch, which is like a second, more dramatic version of the earlier red giant phase. But this time, the energy is produced even faster, so the stage doesn't last as long. Even though there's a shell burning helium, most of the star's energy now comes from hydrogen burning in an outer shell. The helium that forms from this process slowly sinks toward the center of the star. Every once in a while, the helium-burning shell flares up with a sudden burst of energy. These powerful flashes are called thermal pulses, and they happen during the later stages of the asymptotic giant branch. Sometimes, thermal pulses can even continue after the star has left the asymptotic giant branch entirely. Depending on how massive and rich in elements the star is, there might be just a few of these pulses, or there could be hundreds. As the star continues to grow and change during this phase, something interesting happens. Deep inside the star, a large zone of hot, churning gas forms. This turbulent area acts like a conveyor belt, bringing material from deep in the star up to the surface. This event is called the second dredge-up, and in some stars it is followed by a third dredge-up. These dredge-ups can carry carbon from the core to the outer layers of the star, turning it into what's known as a carbon star, a cool, reddish star with strong carbon signatures in its light. But in some cases, a process called hot bottom burning converts that carbon into oxygen and nitrogen before it can reach the surface. The battle between these processes, bringing carbon up and burning it away, determines how bright and colourful these stars appear, especially in star clusters. One well-known type of star on the asymptotic giant branch is the mirror variable. These stars regularly expand and shrink, pulsing with a rhythm that lasts from several tens to several hundreds of days. Their brightness in visible light can change dramatically, by as much as 10 magnitudes, but their actual total energy output doesn't change as wildly. The more massive these stars are, the brighter they become, and the longer their pulsation periods. As a result, they lose mass very quickly, releasing large amounts of gas and dust into space. This makes them hard to see in visible light because they get wrapped in thick clouds, but they shine brightly in the infrared and often show signs of OH-Maser activity, which is a special kind of radio emission from molecules in their outer shells. These stars are rich in oxygen, unlike carbon stars, but both types form through the same dredging up process. Eventually, stars of medium mass reach the very top of the asymptotic giant branch. At this point, they've used up the fuel needed to keep burning their outer shells. Because they aren't heavy enough to start fusing carbon in the core, they begin to shrink and go through a phase known as the post-asymptotic giant branch superwind. During this time, they blow off their outer layers in a massive wind, creating a glowing cloud of gas and dust called a planetary nebula. In the centre of this nebula is an extremely hot core, the leftover heart of the star, which eventually cools down to become a white dwarf. The material that the star sheds into space is rich in heavy elements that were created inside the star. Depending on the type of star, the ejected gas might be full of oxygen or carbon. This gas forms an expanding shell called a circumstellar envelope that gets cooler as it moves farther away from the star. In these cooler regions, dust and complex molecules begin to form. Because of the intense infrared light from the central star, the conditions in the envelope become perfect for master emission, producing bright, focused radio signals from certain molecules. Interestingly, even after a star has entered the post-asymptotic giant branch stage, it can sometimes experience new thermal pulses. These create rare and mysterious stars called born-again asymptotic giant branch stars. These strange stars can take many forms. Now let's turn to more massive stars. In these stars, the core is already so large when the hydrogen shell begins burning that helium fusion starts before the core can become supported by electron degeneracy pressure. So when they expand and cool, they don't brighten as much as smaller stars, but they were already very bright while still on the main sequence. These stars grow into enormous and incredibly luminous supergiants. Eventually, their cores become so massive that even electron degeneracy can't stop them from collapsing. When this happens, they end their lives either as a neutron star or a black hole. Some extremely massive stars, those with more than about 40 times the mass of the Sun, burn so brightly that their intense light blows away their outer layers in powerful stellar winds. Because they lose their envelopes this way, they never become red supergiants. Instead, they stay very hot with a bluish-white colour throughout their lives. The most massive stars we see today have between 100 and 150 times the Sun's mass. If they were any larger, their outer layers would be blown away completely by their own radiation. However, some smaller stars can also avoid becoming red giants if they are part of a close binary system, where a nearby companion star pulls away their outer layers, or if they spin very fast. Fast spinning causes strong mixing, so the star doesn't develop a separate core and outer layer. As a massive star grows older, the core, no longer full of hydrogen, gets hotter and denser as it is fed by the surrounding hydrogen fusing layers. In the most massive stars, the core becomes hot enough to fuse carbon into even heavier elements like neon, sodium and magnesium through something called the alpha process. At the end of helium fusion, the core is mostly made up of carbon and oxygen. In stars heavier than about 8 times the mass of the Sun, this carbon ignites and fuses further, but stars just under this mass may only partly fuse carbon before becoming supported by electron degeneracy pressure. These stars eventually become white dwarfs made of oxygen, neon and magnesium. The exact mass limit for full carbon fusion depends on things like how many heavy elements the star started with, its metallicity, and how much mass it lost during its asymptotic giant branch phase. But in general, full carbon burning begins in stars with around 8 to 9 times the Sun's mass. After the carbon is used up, the core reaches around 2.5 times the Sun's mass and gets hot enough to begin fusing even heavier elements. But before oxygen starts fusing, the neon starts capturing electrons, triggering a process called neon burning. In stars between about 8 and 12 solar masses, this can lead to a runaway reaction and end in a powerful explosion called an electron capture supernova. In even heavier stars, neon fusion happens more calmly. This is followed by the burning of oxygen and then silicon, until the core becomes filled with iron-like elements, which are the end products of fusion. Around this iron core, shells of lighter elements continue fusing. But the final stage happens fast. Once the core has finished turning carbon into iron, it only takes a few hundred years for everything to collapse. During this time, the outer parts of the star barely have time to respond, so the star still looks normal on the outside. Eventually, the iron core reaches what's called the effective Chandrasekhar limit, the maximum mass it can handle before collapsing. This limit is a bit higher than the original Chandrasekhar limit due to various effects like relativity, heat, and pressure from the outer layers. For red supergiants, the effective limit is around 1.34 times the Sun's mass, but in more massive stars it can be over 1.8 times the Sun's mass. Once the iron core hits this limit, it begins collapsing rapidly. Electrons are absorbed by iron nuclei, and the star's core can no longer hold itself up. What follows is a spectacular end. A supernova explosion, or in the case of even more massive stars, a direct collapse into a black hole. When a very massive star reaches the end of its life, something dramatic happens at its core. After using up all its nuclear fuel, the core can no longer support the immense weight of the star pressing down on it, so the core collapses under gravity's pull. This collapse leads to one of two outcomes. If the collapsing core is not too massive, it becomes an incredibly dense object called a neutron star. But if the core's mass is greater than a certain limit, known as the Tolman-Oppenheimer-Volkoff limit, then even neutron pressure cannot stop the collapse, and a black hole forms instead. During this sudden collapse, a huge amount of energy is released. Scientists still do not fully understand how this energy behaves, but we do know that part of it creates an enormous explosion known as a supernova. Depending on the structure of the star and what elements are present in its outer layers, this explosion might be a Type 1b, Type 1c, or Type 2 supernova. One of the most mysterious and powerful events in this process is the release of neutrinos, tiny, nearly massless particles that barely interact with anything. When the core collapses, a colossal flood of neutrinos rushes outward. This was directly observed in the famous supernova called SN 1987A, which exploded in the year 1987. These neutrinos don't just fly away. Some of them interact with the star's material. They can split atoms apart, knock loose neutrons and protons, and transfer heat and motion into the surrounding layers of the star. All of this contributes to the supernova's enormous shockwave, the wave that blasts the outer parts of the star into space. In the densest parts of the collapsing matter, electrons are sometimes forced to merge with protons, creating even more neutrons. As the shockwave rebounds, it slams into surrounding material, bombarding it with these loose neutrons. Some of the atomic nuclei catch these neutrons, leading to the creation of heavy elements even heavier than iron, and including radioactive ones, possibly all the way up to and beyond uranium. Now, it is true that older, non-exploding stars, especially red giants, can also create some heavy elements using neutrons released in slower side reactions. But the kinds and amounts of heavy elements made in red giants are quite different from those made during a supernova explosion. And interestingly, neither type of process alone can explain all the heavy elements we find in our solar system today. That's why scientists believe that supernovae, collisions of neutron stars, and mass ejections from red giants all play a role in creating and spreading these heavier elements across the universe. The energy released during the core's collapse not only makes heavy elements, but also hurls them outward at tremendous speeds, much faster than the escape velocity of the star. This is what powers the incredible brightness and force of a Type 1b, Type 1c, or Type 2 supernova. However, even today, scientists are not entirely sure how enough energy is transferred from the collapsing core to the rest of the star to cause such a powerful explosion. Computer models can explain part of it, but not all. One promising idea involves neutrino oscillations, the way neutrinos change types as they move through space. These oscillations may help transfer more energy, both by changing the total energy in each kind of neutrino, and through strange effects predicted by Einstein's theory of general relativity. Some fascinating clues come from binary neutron stars, systems where two neutron stars orbit each other. These systems must have come from two separate supernovae, and their behavior gives us insight into the differences between various types of supernova explosions. In particular, if a star's core is mostly made of oxygen, neon, and magnesium, the supernova it produces may be observably different from one coming from a core made mostly of iron, even if they explode with similar energies. Among the most extreme cases are the largest stars in the universe. The most massive stars known today can sometimes be completely destroyed in an especially powerful kind of supernova caused by something called pair instability. In this rare type of explosion, the energy released is greater than the gravitational energy holding the star together, so the entire star is blown apart, leaving behind no black hole at all. Even more massive stars that existed billions of years ago were so large that, instead of exploding, they collapsed instantly into black holes due to a process called photodisintegration, where their intense heat broke apart atomic nuclei and triggered total collapse. After a star dies and burns up its fuel, what's left depends on how massive it was during its life. A star with a mass similar to our Sun, about 1 solar mass, will shrink into a white dwarf, a very dense object with a mass of about 0.6 solar masses packed into a space no bigger than the Earth. White dwarfs stay stable because the gravity pulling inward is balanced by a special kind of pressure that comes from electrons being squeezed together. This is called electron degeneracy pressure, which is a result of the Pauli exclusion principle, a rule in quantum physics that says 2 electrons cannot occupy the same state at the same time. Interestingly, white dwarfs behave in a counterintuitive way. The more massive they are, the smaller they get. Once they form, white dwarfs don't burn any more fuel. They simply shine by releasing leftover heat into space. This cooling process takes billions of years. When a white dwarf is newly formed, it is extremely hot. Its surface can be hotter than 100,000 Kelvin, and its core is even hotter. In its first 10 million years, a lot of its energy is lost through the emission of neutrinos. After about 1 billion years, most of its heat has been radiated away, and it continues to cool. The makeup of a white dwarf depends on how massive the original star was. A star with a mass between about 8 and 12 times the mass of the Sun will go through a phase where it fuses carbon into elements like magnesium, neon, and small amounts of others. If such a star loses enough of its mass before collapsing, it can leave behind a white dwarf made mostly of oxygen, neon, and magnesium, as long as the carbon burning is not too violent to cause a supernova. Stars with masses around that of the Sun don't get hot enough to burn carbon, so they form white dwarfs made mostly of carbon and oxygen. These white dwarfs are not heavy enough to collapse on their own, unless extra matter is added to them later. On the other hand, very small stars, those with less than half the Sun's mass, can't even ignite helium fusion, and will eventually leave behind white dwarfs made mostly of helium. Over a very, very long time, a white dwarf cools so much that it becomes a cold, dark object known as a black dwarf. However, the universe is still too young, less than 14 billion years old, for any black dwarfs to have formed yet. But if a white dwarf gains more mass, either by merging with another star or by pulling in material from a nearby companion, it can become too heavy. If it grows past a certain point, called the Chandrasekhar limit, which is about 1.4 solar masses, electron pressure can no longer support it. What happens next depends on its composition and core temperature. The star may collapse into a neutron star, or the heat may trigger runaway fusion of carbon and oxygen, causing a bright Type 1a supernova. Type 1a supernova can shine many times brighter than the Type 2 supernova caused by massive star death, even though they release less total energy. No white dwarf can exist beyond the Chandrasekhar limit unless it's spinning extremely fast. Then centrifugal force might help support the extra weight. Sometimes, in a close binary system, a white dwarf can slowly pull hydrogen from its larger companion star. This gas builds up around it, and once it gets hot enough, the hydrogen suddenly fuses in a violent burst. This event is called a nova. Unlike a supernova, the white dwarf survives a nova and can go through the cycle again. Normally, when we look at atoms, the tiny building blocks of everything around us, they are made up mostly of empty space. Most of their volume comes from the cloud of fast-moving electrons that surround a tiny dense centre called the nucleus. To understand how small the nucleus is compared to the whole atom, imagine this. If an atom were as big as a football stadium, its nucleus would only be about the size of a speck of dust floating in the air. But something extraordinary happens when a massive star reaches the end of its life, and its core collapses under its own immense gravity. the pressure becomes so incredibly high that it forces the electrons and protons inside atoms to combine through a process called electron capture. This process creates neutrons. Once the electrons are gone, electrons that normally help keep atomic nuclei apart, there is nothing left to stop the neutrons from being crushed tightly together. What results is an object made almost entirely of neutrons, packed together in a super dense ball, like one gigantic atomic nucleus. Around this dense core there may be a thin shell made of super compressed matter, usually made mostly of iron, unless other types of matter fall onto it later. These remarkable objects are called neutron stars. They are incredibly small compared to normal stars. Each one is only about 10 kilometers across, which is roughly the size of a large city. But they are unimaginably dense. A single teaspoon of neutron star matter would weigh more than a mountain on Earth. The neutrons inside resist being crushed any further because of a quantum rule called the Pauli exclusion principle, which says that no two neutrons can occupy the same quantum state. This force is similar to the one that keeps white dwarfs from collapsing, but the neutron version is much stronger. When the core of a dying star becomes a neutron star, something else amazing happens. As the star shrinks, it starts to spin faster and faster, just like a figure skater spinning more quickly when pulling in their arms. This happens because of a law in physics known as the conservation of angular momentum. Some neutron stars spin incredibly fast, making hundreds of complete rotations every single second. The fastest ones spin in about 1.5 thousandths of a second, which means more than 600 spins in just 1 second, while others may take a few seconds to spin once. Now, some of these spinning neutron stars have magnetic poles that sweep past Earth like the beam of a lighthouse. Every time the beam points toward us, we detect a pulse of energy, often in the form of radio waves. These pulsing neutron stars are called pulsars, and they were the first type of neutron star ever discovered. While they usually emit radio waves, some pulsars also give off visible light, X-rays, or even gamma rays. However, not all collapsing stellar cores stop at the neutron star stage. If the remaining mass of the core is too high, greater than about 2 to 3 times the mass of our Sun, although the exact number is still uncertain, even the pressure from neutron degeneracy is not enough to stop the collapse. In that case, the core keeps shrinking until it becomes a black hole, an object so dense and with gravity so powerful that not even light can escape from it. Black holes are predicted by Einstein's theory of general relativity. According to this theory, once something crosses the boundary around a black hole, called the event horizon, it can never escape. No matter, no light, and no information can come back out. However, some new theories in quantum physics suggest that this rule might not be absolute, and there could be tiny effects that allow some information to leak out. Today, the existence of black holes is strongly supported, not only by theoretical predictions, but also by many kinds of astronomical observations. Scientists have detected black holes by watching how stars orbit around them, by measuring gravitational waves, and by observing the bright X-rays emitted by hot matter falling into them. Even now, scientists do not completely understand what happens during a core collapse supernova, the powerful explosion that often happens when a massive star dies. It is still a mystery whether some stars can collapse directly into black holes without producing a visible supernova, or whether they first form unstable neutron stars that later collapse into black holes. Also, it is not fully known how a star's starting mass and chemical makeup determine whether it becomes a white dwarf, a neutron star, or a black hole. To solve these puzzles, astronomers must study many more supernovae and the remains they leave behind. To better understand how stars live and die, scientists use something called a stellar evolutionary model. This is a set of complex computer programs that simulate how a star changes from the moment it is born until the moment it becomes a remnant like a white dwarf, neutron star, or black hole. These models begin with basic information about a star, like how massive it is and what elements it contains. The models also use well-understood physics rules, such as the idea that the forces inside the star must balance to keep it from collapsing. The models then calculate how the star's brightness and surface temperature change over time. Using this information, the models show how the star moves across the Hertzsprung-Russell diagram, a special chart that astronomers use to track the life stages of stars. These models are extremely useful. They allow scientists to estimate how old a star is, just by comparing its current properties to the results of the models. In this way, astronomers can piece together the life story of a star and better understand the fate that awaits it. Imagine the universe had its own Hall of Fame for the biggest, brightest, and most mind-blowing stars ever discovered. Without a doubt, standing tall and proud in that imaginary gallery would be a truly enormous and mysterious star known as the Behemoth. This is not just any star. It's a bloated, burning monster that doesn't even live in our Milky Way galaxy. Instead, it hides far away in a neighbouring galaxy called the Large Magellanic Cloud, which is like a companion galaxy orbiting ours. The Behemoth is so huge, so bright, and so puzzling that it's forcing scientists to rethink what stars can actually do. It was first discovered back in the 1970s by 3 astronomers named Westerlund, Olander, and Hayden. The star's name, WH-G64, comes from the first letters of their names. Even in the early days after its discovery, the Behemoth grabbed attention because of its jaw-dropping size. Astronomers believe its radius, the distance from the centre to the outer edge, is around 1,500 times larger than the Sun's. To help you picture that, if this star replaced our Sun in the centre of the solar system, its fiery surface would swallow up Mercury, Venus, Earth, and Mars, and it would reach almost all the way to Jupiter's orbit. That's truly enormous. To make it easier to imagine, think of the Sun as the size of a tennis ball. Now imagine the Behemoth as a sphere the size of an entire football stadium. That's how much bigger it is. But size isn't its only superpower. The Behemoth also shines with incredible brightness. It gives off nearly 280,000 times more light than our Sun. Yet strangely enough, we don't see all that light directly. That's because this titanic star is wrapped in a thick, dusty cloud shaped like a donut. This dusty shell, made of gas and ash thrown off by the star itself, blocks a lot of its light and makes it hard for astronomers to observe. But this dusty veil is more than just a cosmic cloak. It's a warning sign. It shows that the Behemoth is probably in the late stages of its life. The material the star is throwing off is not just a small puff. It stretches almost an entire light year across, which is nearly 6 trillion miles. This cloud is slowly drifting outward, pushed by fierce stellar winds and the star's unstable outer layers. It's like the star is shedding its skin as it prepares for a dramatic end, maybe a massive explosion known as a supernova. That kind of mass loss is common in stars that are burning through their fuel faster than they can keep up. The Behemoth is burning bright and fast, and it won't be able to keep it up forever. And here's another twist. For a star that burns so brightly, it's surprisingly cool on the surface. Its temperature is only about 3,000 to 3,400 Kelvin, cooler than most stars, and low enough to place it in the category of red supergiants. These are giant stars that have swelled up near the end of their lives, glowing red due to their lower temperatures. But even among red supergiants, the Behemoth is strange. It may be sitting at, or even beyond, a physical boundary known as the Hayashi limit. This limit tells us that a star of a certain size and mass shouldn't be able to stay stable if it gets too cool. And yet, the Behemoth seems to be breaking that rule, which has left astronomers scratching their heads in confusion. Is it really one single star? Or could it be 2 stars orbiting each other so closely that they look like one? Because of the thick dust and its great distance, we're not sure. Some scientists think there might be a second star hiding, maybe a hot, bright blue O-type or B-type star just out of sight. If that's true, the Behemoth could actually be a binary system, 2 stars in a close relationship possibly interacting and influencing each other. That could help explain why it's losing so much material. Perhaps the companion star is pulling it away or stirring things up through gravity. But for now, no second star has been confirmed. It remains a mystery. Another fascinating part of this story is where the Behemoth lives, in the Large Magellanic Cloud. This galaxy is famous for housing unusual and massive stars. One possible reason is that its chemical makeup is different from that of the Milky Way. It has fewer heavy elements, what astronomers call metals, and that could allow stars there to behave in strange ways, growing bigger, evolving faster, and dying more dramatically than stars in our own galaxy. The Behemoth might be the perfect example of this. It's a cosmic giant born in an environment that allowed it to become far larger and more extreme than we would normally expect. In many ways, it's a star that challenges the rules, and one that continues to fascinate and puzzle astronomers today. The Behemoth star isn't just bigger than our Sun, it's much bigger. And when it comes to brightness, it doesn't just outshine the Sun a little, it outshines it in every possible way scientists can measure. This enormous star is estimated to shine about 280,000 times brighter than our Sun. That makes it one of the brightest stars ever discovered in the entire universe. But what does that actually mean in everyday terms? Let's break it down. The amount of energy a star releases every single second is called its luminosity. Our Sun has a luminosity of about 3.8 times 10 to the power of 26 watts, which is enough to warm our planet, drive the weather, and keep life going from a distance of about 150 million kilometers away. Now imagine taking that same amount of energy and multiplying it by 280,000. That gives us a staggering number, around 1.064 times 10 to the power of 32 watts. That's such a massive amount of energy it becomes nearly impossible to imagine. It's not just the difference between a candle and a campfire, it's more like comparing a tiny matchstick to the detonation of an entire planet. The Behemoth star is a roaring furnace in space, so intense and so powerful that its light alone reshapes the environment around it. This blinding brightness isn't just an impressive statistic, it has real effects on the star's surroundings. The radiation it gives off is so powerful that it pushes away the star's own outer layers. This creates violent stellar winds, streams of particles flying outward, and forms giant shells of dust and gas that expand into space like ripples from a cosmic explosion. Most of the light coming from this gigantic star isn't even visible to the human eye. It shines mostly in infrared and visible wavelengths, but the light is so intense that it could be spotted across millions of light years, even from other galaxies, if there wasn't a thick, murky cloud of dust blocking our direct view. That's where infrared telescopes come in. Since regular optical telescopes can't see through the dust, astronomers use powerful instruments like those at the Very Large Telescope in Chile to peer through the veil. These telescopes pick up the star's infrared light and study its spectral fingerprints, unique clues that tell us how much energy the star gives off, what elements are swirling in its atmosphere, and how fast it's losing its outer layers to space. But all this dazzling brightness comes at a price. The Behemoth star is not young. In fact, it's near the end of its life. Stars that burn this bright are also burning through their fuel at an unsustainable pace. They live fast and die young. While our Sun still has around 5 billion years left before it reaches the end of its life, the Behemoth star will likely survive only for a few million years, a mere blink when compared to the age of the universe. The extreme energy it pours out is a sign that it's living on borrowed time. It's like a runaway nuclear reactor operating at full blast, knowing the end is coming soon. And that brightness? It's not just something to admire, it's dangerous. The intense radiation it gives off can split apart molecules, destroy DNA, and evaporate entire atmospheres. If there were a planet unlucky enough to orbit too close to this monster, life wouldn't stand a chance. The radiation would fry everything in moments. In truth, the Behemoth star is not the kind of star you'd want as a neighbour. It's not cozy, it's not gentle, it's a brutal force of nature, flooding space with heat, light, and destruction. Even stranger, this star doesn't shine at a constant rate. It goes through waves of brightening and dimming, which scientists believe are caused by instabilities inside its core. Each flicker and change in brightness could be a signal. Maybe it's collapsing, maybe it's preparing to explode, or maybe something even more mysterious is happening deep inside. So why do scientists spend time studying something so extreme, so unpredictable, and so terrifying? Because studying the Behemoth star helps us understand the lives and deaths of the largest stars in the universe. This kind of star is incredibly rare, and its intense light gives us a rare window into a process that only happens in the most powerful corners of the cosmos. It's like watching a slow-motion replay of a cosmic disaster, one that reveals how galaxies grow, how heavy elements are created, and how the universe transforms over time. In its final, furious blaze, the Behemoth star tells a story billions of years in the making, and helps us uncover the secrets of the stars themselves.